TensorFlow or PyTorch are two of the most popular frameworks to train and use deep learning model. But what about OpenCV, the most popular library for image processing and computer vision tasks? Can you use it for deep learning tasks? And the answer is yes, you can, using the DNN module inside OpenCV. And this is what this course is all about. In this crash course, I'm going to show you how you can leverage many different deep learning models that have been trained with TensorFlow or PyTorch and use it inside OpenCV. And more on that, I'll also show you how to train custom deep learning models and then deploy it inside OpenCV, and how to train custom object detection models with TensorFlow Object Detection API and then use it directly inside OpenCV. And I'll be discussing many other intricate details on how to best utilize this DNN module and use its various capabilities. So stick around for this entire course and let's get started. So let me quickly go over the introduction of this DNN module inside OpenCV. So this module was released with the OpenCV 3.0 version, and today it has evolved a lot. So this is how this will work. You will train models inside TensorFlow or PyTorch framework or some other, and what you will do then is that you will deploy those models inside OpenCV. So these libraries, TensorFlow and PyTorch, will be used for training and OpenCV will be used for prediction. Now, if there are already models out there that are trained with TensorFlow or PyTorch, you will just need to plug in those inside OpenCV. So what are the benefits of using this sort of an approach? Why not just use TensorFlow or PyTorch directly? So here are some key differences and benefits that you'll get when you're using OpenCV as a prediction framework. So with OpenCV, what will happen is that you will get rid of the whole TensorFlow and PyTorch overhead. So the code will be a lot simpler and compact, and it will just be OpenCV that you will be dealing with in the final application. Second, someone who's not even familiar with the framework like TensorFlow, he can still use OpenCV to do predictions on it, and he doesn't need to understand how the whole framework works, how it was trained and whatnot. Just use OpenCV and plug in the model and directly get predictions out of the deep learning model. Next up, with TensorFlow and PyTorch, you can use NVIDIA's GPUs, but with OpenCV, not only can you leverage NVIDIA's GPUs, but you can also leverage OpenCL based Intel GPUs. Furthermore, some benchmarks show that OpenCV's DNN module runs slightly faster in CPU compared to other frameworks like TensorFlow or PyTorch. So these are some of the benefits that you get when you use OpenCV directly and just plug in a model trained with TensorFlow and just roll with it. So this is what you get. So in summary, you train a deep learning model with a framework like TensorFlow, and when the model is finally trained, just throw away the framework, plug the model directly in OpenCV, and you're all set to go. And one of the other key advantages of using this sort of an approach is that when you're using edge devices like Raspberry Pi, which has limited memory constraints, then you can get rid of very heavy frameworks like TensorFlow and PyTorch and just use OpenCV in the final application. So this is really useful in these kind of scenarios. So one limitation that you should know about is that OpenCV's DNN module can't be used for training deep learning models. And that is sort of okay, because PyTorch and TensorFlow are awesome when it comes to training deep learning models. I don't think I'll be shifting to another framework for training purposes. But for inference on CPU, OpenCV is a great framework. And here is the full list of all the frameworks that you can use to train deep learning models. There's Caffe, TensorFlow, PyTorch, and the darknet. And then you can use also ONNX models, which is the intermediate format. You can convert TensorFlow PyTorch model into ONNX, and this is really useful because later on I'll show you how you can mitigate and solve some problems with this sort of an approach. So these are all the models that you can use to train, and here is a list of the variety of models that are available in the OpenCV model zoo that you can directly use and plug in the DNN module. So we have different categories. We have some models in classification, some models in detection, segmentation, some other models like facial and gesture analysis, image manipulation, and text detection and recognition. So there is a variety of models that you can use inside the DNN module. And this is not even the full list. But for our purpose and for this particular tutorial, in the first part, I'm going to be using the DenseNet model for doing image classification. Now this DenseNet model has been trained on the ImageNet dataset, one of the largest datasets of images. Now this dataset contains 1000 different object classes. This means that the model, the image classification model that we'll be using, will be able to classify between 1000 different things. So now let's get started. So this is the Jupyter notebook that I'll be using today for this tutorial. So as I said, in this particular part, I'm training an already trained DenseNet model on ImageNet, and I'll be showing you how to use it in OpenCV. Later on in this crash course, I'm also going to show you how you can train a custom image classifier and then use it in OpenCV, and also how to train a custom object detector with TensorFlow Object Detection API and then use it in OpenCV directly. So this will be a full-on crash course. This is the first notebook. There will be in total 3 notebooks that I'll be going over in this crash course. Now let's just start with this one. So what you're going to do first is you're going to import all the required libraries. I'm working with NumPy, OpenCV, and Matplotlib as usual. There are some helper libraries in between. So let's load them up. Now the first thing that you need to do is you need to load up the class labels. So this is a text file that I have called synsetwords.txt. Let me pull that up. So this is the file I'm talking about. So as you can see, this is the whole list of all the 1000 classes in the ImageNet. And this has a particular format. So like there's an ID number, and then there's a name of the class, and then there's some alternative names like this. So for example, for goldfish, there is a biological name and then some other names. For a white shark, there's some alternative names like white shark, man-eating shark, and I don't know how to pronounce this one, but yeah, there's there. So yeah, for someone, for like hens and you know, like the other there's just a singular name, but like for other animals, they are like multiple names, like a biological name and the actual name and the ID number. So what I'll do first is just read up all the names in a list, in a Python list first, and then I'll process the list in a way that I only get the first of each class. So I'll extract bald eagle from this whole line, and then I'll just discard the rest. Similarly, I'll do this for all the 1000 classes here. So let's do that. So what I'm going to do is just I'm going to open the file and read it and strip the extra spaces, split it with a new line. So I'm going to get rows, a Python list where all the classes are in a single line, and I'm just going to print out a few lines. So I'm going to run this. Oh, I think I've already ran this before, but anyways, let's run this again. And so here are the results that you will see. Number of classes in total is 1000, and this is how the list looks like, as we already have seen in the text file. So now what I'm going to do is just I'm going to process them, and I'm going to use regex to separate that first word from all of the rest, and then I'm going to store it inside another list called classes. And then I'm going to just show you first 20 classes. So this is what our new list looks like: tench, goldfish, great white shark, tiger shark, hammerhead, etc. So this is all the 1000 classes neatly packed in a Python list, and this is what we need. So yeah, now we've had the list. What we're going to do now is just start loading up the deep learning model. So this is how this works. To load up the deep learning model, you will be using the DNN module, and to use the DNN module, you will do this cv2.dnn, and this way you'll access the DNN module. Inside this DNN module, we have some functions. So for reading up models in Caffe framework, you'll use dnn.readnet from Caffe. For reading model in TensorFlow, you'll use readnet from TensorFlow. For PyTorch, you'll use readnet from Torch. So this is how you're going to load up models from different frameworks. Now, what I'm going to do now is I'm going to use readnet from Caffe, because the model that I'm using right now is TensorNet 121, and that model has been trained in a Caffe framework. So for that, what I'm going to do first is I'm going to specify a path to where all the weight files are present, model TensorNet121.Caffe model, and then I'm going to also specify a path where the whole architecture of the model is present. So these are 2 different files that you will need every time you're working with a model. So this file contains all the trained weights. Whenever you train a deep learning models, there are some parameters that keep updating, and you use those parameters and then you pass an image or any data through those parameters, and some maths happen. I'm just going to say some maths happen because I'm not going to explain the whole deep learning workflow at the moment, but some multiplications happens, and then after the data has passed through, what comes out as the output is the final predictions that you need. So this is all the stored parameters. And then this is the architecture, which describes how the model is structured, how many layers, how many nodes, what types of layers are present, and whatnot. So this is all the architecture. This is a lightweight file because it's simply a text file, but this is a model. Now this model is mostly the like the biggest file out there when you're using a deep learning like framework model. So and there's a nice description of this. Proto.txt, it's the file path, it's the path to a .proto.txt file, which is a text description of the architecture of the model. Now this is proto.txt.txt file, but and this is for Caffe. For different frameworks, there may be different extensions. For example, for TensorFlow, it may be a different one. And then this is the Caffe model. It is the path to a .caffe file, Caffe model file, which is like the actual deep learning model. And I've explained this here. And so yeah, and note if you're using So one other thing, if you're using a model trained in TensorFlow, then you'll specify the weights first and the architecture second. Right now, as you can see, I'm specifying the architecture and passing in as a first parameter, and then I'm passing the weights as a second parameter inside this readNet from Caffe function. But if you're using readNet from TensorFlow, you'll do the reverse. You'll specify passing the weights first and the architecture second. So this is how this works, and let me just run this up. And now what happens is that our model is loaded in this net variable. And what I'm going to do now is just read an image, process an image, and then pass that processed image inside this model. So we're going to see what happens next. So now what I'm going to do is just read a sample image in OpenCV using cv2.imread. I have an image stored jammer2.jpg inside this images directory, and then I'm just going to display it with mat.lib, so you can see what are we going to classify. So as you can see, this is a rabbit or a hare, and I'm gonna pass this image inside this image classifier. So I have this image, but before passing the image inside our deep learning model, you always need to pre-process an image. Now to pre-process an image, you already have a function, a helper function inside the DNN module called cv2.dnn.blob from image. And there's another variant called blob from images if you're working with batch of images at once. Now, to be honest, this function is not as extensive as it should be, because oftentimes I've seen that like these things that you can do inside this function, and these are all the pre-processing options that you have. These are not all of it that you always need, and sometimes I have to include custom pre-processing operations with NumPy to properly pre-process an image before passing it into a model. But for this particular use case, this is a really simple use case. This is just a classification scenario. I'll be using this function. But sometimes I'm going to show you in later on tutorials when you need to use custom operations that do not come with this packaged function. Anyways, let me just go over these options that you have. So the first parameter that you pass in is obviously the image that you will be using, that you will be performing pre-processing operations on. The second one is the scale factor. Now this is a value that you're going to multiply the image by. Now what will happen after the multiplication is that normally what we do is that the authors, when they're training deep learning models with images, they pre-process the image in a way that the range of values in an image from 0 to 255 goes to 0 to 1. And this is the same thing that we'll need to do before passing the image to the model, because this is how the model has been trained on. So we'll multiply the image by 1 divided by 255, and this will make the image have the values in the range 0 to 1 instead of 0 to 255. So here you will see 0.0117, and this is the same value you get when you multiply 1 by 255. So because we're not dividing, this is a multiplication factor. So if it was a division, I'll just be including 255 to divide all the images by 255. But this is just a scale factor that you multiply with. So it's 1 divided by 255, which is the value that you multiply all the pixels, all the values in the image. So this way you get the image in the range 0 to 1. And yeah, So this is the scale factor, and then we have the size. What is the size that this function should resize the image to? So most of the models that we use is like takes the image in a specific size, and for this model it's 224 by 224. It's a squared image, and this is the width and the height that the image will be resized to. And then we have this mean value. This is the mean RGB value that will be subtracted from the RGB channels of the image. This is another pre-processing scheme that the authors of different frameworks, or different models follow, and it helps in training too. So what they do is that they subtract the mean R and GB values of the whole data set from each and every image. So this is the thing that we have to repeat when we're doing the inference or the prediction. So these are the values that will be subtracted from the RGB channels of each image that we pre-process. So this is what we're doing. And then we have two other variables, swap RB. This is a Boolean variable which specifies if we need to reverse the image channels. Since TensorFlow and PyTorch frameworks train models with images in RGB, so we need an OpenCV reads an image in BGR. So we need to account for that. So in this, since we already have loaded image in BGR, and PyTorch and TensorFlow train works with images in RGB, so we reverse those channels. So we set our swap RB equals to true. By default it's false. So we need to do that. But since now we're using a Cafe framework, and Cafe framework also follows the BGR convention like OpenCV does, so we don't need to swap the red and blue channels. So we need to we can still work with the BGR mode. So I don't need to set the swap RB to true, because like I said, I'm using the Cafe model. If you're using TensorFlow, you need to set it to true. Otherwise, you'll see a drop in accuracy. And this is really important, because I've seen some people, they used TensorFlow models in this and use blob from image, but they don't set the swap RB value to true. And this way, you'll use some accuracy. You lose some accuracy points. Finally, we have this crop function. And this is another pre-processing technique where we're telling where the author decides if he just want to strictly resize the image into a strict size. For example, I'm gonna use CV2.resize to directly resize the whole image into 224 by 224, or I'm gonna cleverly resize this in a way that I'm gonna pick up the smallest dimension, I'm gonna resize it into 224, and I'm gonna just crop out the other dimension. So this way the aspect ratio of the image is maintained. And this is a neat looking image. So it depends how the author trained the image. If it followed this scheme, this particular scheme, you'll set this to true. Otherwise, you'll let it be false. I think by default it's false. Yeah. So by default it's false. So we'll let it be because the author didn't use this sort of a pre-processing scheme, and we're just going to roll with this one. So now after I run this, we have a blob, and this blob is actually a 4-dimensional blob. So we have this, we have the image, we resize the image into 224 by 224. The image has 3 channels RGB, and there's one extra channel that we add. So this is normally done because oftentimes when we're working with deep learning models, we're working with batches of images. So we need to perform prediction on batches. So this is why we have added an extra dimension, because the deep learning model that's going to predict on this is going to expect a 4-dimensional array. Again, if you actually want to work on batches of images, use this function blob from images, and you're going to pass an array of images instead of a singular image. All right, let's move on. So now that we have a pre-processed image or a blob, we're going to set up the network. So this is how this happens. Remember that we have loaded the deep learning model in this .NET variable, and now I'm going to call net.setInputBlob. So this is going to set up the pre-processed image as the input to this network. And now this is where all the pre-processing will happen. Let me just run this up. I don't think I run this. So now this is where all the pre-processing will happen, or maybe sorry, this is where all the computation will happen of the network. So here what will happen is that we'll perform a forward pass. So an image will enter the model, and all the operations will happen, and then the output will come out here. So all the main computation and most of the time will be will happen here. So that's why I'm also calculating the time that this cell will take to run. So let's run this and see the time it takes. 114 ms. Let me run it again. So 50 in the first iteration it normally takes more time. So as you can see, on average it takes 53.9 milliseconds to run this model on a sample image. And this tells you that you can run this model in real time. So you'll get approximately like 20 FPS. So because like in a single second you have 1000 milliseconds and you can divide by 53.9, you'll get somewhere around 20-ish frames per second when you run this model on an image. So this way you'll see clearly that this model is capable of running in real time. And let's see the total number of predictions that we get. So now we have all the output predictions inside this output variable, and now all we need to do is just post process this output variable and grab the predictions out of it. So this is what normally happens. We get an image, we pre-process it to make it ready for the model. We pass it into the image, we get the predictions out. And now we can't just consume those predictions. We need to post process it in a way that we extract the meaningful things that we need. So here what we need is the accuracy and the label of the class that is the model thinks that the image contains. So now I'm just gonna print out the total number of the total array length, which is 1000, and it should be 1000 because the model is predicting and it's trained on 1000 classes. And I'm just going to look at a few outputs. Let's take a look at some of the outputs. So this is what I'm getting, and this must be if this is confusing to you, it's okay. Now these are some things which are called class scores. So each number represents a particular class score for each class. So now what we're going to do is convert these class score into probabilities, and the way that we're going to do that is by applying a Softmax function to get those probabilities out. So this is how I'm gonna apply a Softmax function. I'm gonna first reshape the output, and then I'm gonna apply this formula to get the probabilities from these class scores. And this is a Softmax function which I'm doing here by NumPy. And when I run this, I've converted all the class scores in this output into class probabilities. Now let's take a look at this output. So this is what you get, and this is more intuitive. You can see that for this the first class you have a very low probability, 5.7 exponent minus 6, 3.7 exponent minus 5, and like that. So these are really low probabilities for the first 4 classes, which tells you probably the image does not contain the first 4 classes, and we already know it does not contain those classes because the first 4 classes is what is it? Tench, goldfish, great white shark, tiger shark. Obviously this is not a shark or a fish, it's a hare or a rabbit. And now what we're gonna do now is that now I'm gonna call this function np.max and pass in the whole probability links. Now np.max is gonna give me the maximum probability, and I'm gonna print that out. So here's what I'm getting. I'm getting 59.9, so 0.59. Remember, this is in the range 0 to 1. So 0.599 means I'm 59.9% sure that this is the class. Now I have the maximum confidence, but which index has the maximum confidence? We have 0 to 1000 indexed classes. So this is where I'm going to call np.argmax. This is going to give me the location of the whole 1000 arrayed list, where exactly the maximum value is located at. So I'm going to grab the index. Now this tells me that the 331st value is the one which contains this highest value. So now I have the index. I know that out of those 1000 array output, 1000 classes, the output, the 331th item has the highest value, and that highest value is this value 0.599. So now what I'm going to do is just I'm going to use this index, and I'm going to put this inside this classes list. So I already have this classes list, which is a list which contains all the names. Remember this list which I created here. So this is the classes list which contains all the 1000 classes, and inside this list I'm just going to put this index value 331, and I'm going to get the exact label out. So if I put this, I'm going to get the hare, which is like the rabbit. So here's what's happening. I'm telling this classes list to tell me what is the name or the item or the class name you have at the location 331, and it tells me that we have a hare here. So now I got what I want. I have the probability 59.9% is the highest probability, and the class that has the highest probability is the hair. So now I'm just going to use cv.put text, passing the image, passing the label and the confidence. I'm just going to multiply this by 100, so I can print out the percentage of it, and then I'm just going to display the results with matplotlib. Let's see the final results. So label, hair, and 59.98% the confidence of this image. So this is how this whole or scheme or deep learning DNN module works, and that's it. All I'm going to do now is I'm going to create a function, put all of the code above neatly inside those functions, and test it out on other images. And just to recap again, let me show you the whole process that happens here. And this is what we do. We read an image and the target classes. We initialize the DNN module with the architecture and the model parameters. We then pre-process the image. I think this step is missing in this particular image. So we pre-process an image, and then we pass the pre-processed image inside the module and perform a forward pass on it. And then finally we post-process the results to grab the things that we're looking for. So that's the whole process of the DNN module. And remember, this whole process will stay approximately the same for any model that you use. The only things that change is the pre-processing steps and the post-processing steps. Because here now we worked with the classification model, and for classification model the pre-processing or the post-processing is really same. But for other sort of models like the object detection model, the image colorization model, the super resolution model, image segmentation model, so for those sort of models the post-processing steps are a little bit more involved. But it's simple enough, and in fact I've covered some of those models in bleedia.com tutorials in my website, and I'll be covering some of those in later tutorials on YouTube. So anyways, let's wrap this up, put all of the code that I've shown you in a detailed manner in this. So I'm creating two functions. I'm calling first one the initialization function and the second one the classify function. And what I'm going to do in the first function is that I'm going to put all the things that are going to be initialized here. So here I'm going to put the text file that contains the class names. I'm gonna read up that text file, clean up it and process it. I'm gonna load up, initialize the model with the weights and the architecture file, and I'm gonna pass those as a hyperparameter. So this way, I'm setting this function up in a way that even if you want to test out a different model, a different classification model, you can just use the same exact functions, pass in a different weight name, pass in a different architecture name, and you're all set to go. But make sure that model is also trained on the ImageNet classes. Otherwise, if you have different classes, pass in the text file name of those particular classes. And obviously, you'll need to change the pre-processing scheme. But like for most of the image classification models are trained on the ImageNet class. Anyways, so this function can be used for different for other models too. So anyways, let me run this. Now the model will be initialized when I run this function. Now let's take a look at the classify function. It's the same function. It contains the same things that I showed you above. We have an image. We have a variable called return data. I'll tell you about it. And we have this size. So this is just for drawing purposes. So what's the font size that I'm going to draw on the final image with the predictions? So this is what the size variable is. And so what happens is that I just get the image, I pre-process it, I set the input, I make a forward pass out of it. Now I grab the output, I post-process it to get the probabilities, I grab the confidence and the label by using that probabilities. And then when I've got those two things, I put those two things and with cv2.putText function on top of the image. So I annotate the image with the predictions. And if this return data variable is set to true, I return the image and the text results. Otherwise, I show it with matplotlib. So I'm doing this, and this is a common thing that I normally do because I want this function to work on images as well as on videos. So when I'm working with videos, I don't want to display each frame with matplotlib. I just want to get the results back. So to show it with cv.imshow function in a video loop. So that's why I have this variable here. When I'm working with images, this variable is set to false. And when I'm working with videos, this variable is set to true. So this is how this works. Let's run this, and I'm going to initialize this classifier, and then I'm going to test it out on multiple images. So I'm just reading an image, classifying it. I'm reading an image and classifying it. I'm reading an image and classifying it. So let's run this. So this is a sports car and it's labeled as a sport car, correctly 74.36% accuracy, and then 79.94, it's labeled as an Egyptian cat, which it is. And let's test out another image, a green lizard, it's accurate again. Another image here, 59, it's the same image as above. So yeah, accurately done. Lastly, I have this optional cell that you can test this model on a video loop. So let me just quickly explain this. What's happening here. So I have this variable called FPS, which will calculate the whole FPS. Initially, I'm setting it to 0. I'm calling the initialize function to initialize the model. Then I'm setting up the video capture function and passing it 0 to use the first webcam here. And then I'm going over a loop. I'm starting a loop. And in this loop, I'm gonna set up a timer to calculate the start time. So this is just for calculating the FPS. And then I'm reading the video capture, like object frame by frame to read from the webcam. And if the frame is not read correctly, I'm gonna break out of the loop. And if it is, I'm just gonna laterally flip in a way so I see a mirror image. Otherwise, it's an inverted image. So then what I'm gonna do is take the image and pass it into the classifier function. The classifier function is gonna do all the classification and it is gonna return to me the image, annotated image. And then I'm gonna, show the annotated image and the FPS, calculated FPS on top of it. And then I'm gonna just call the CV.imshow function instead of matplotlib to show the image in a video loop. And this is where the FPS calculation is happening. So frames per second, how fast the video is happening. And then if the user presses the Q button, I'm gonna break out of the loop. I'm gonna release the camera. I'm gonna destroy all the windows. So this is a normal video loop that I do when I'm working with videos. If you want to understand more, or if you want to go over it, be sure to watch the crash course in OpenCV. I have it published on YouTube and also have a detailed blog post on it on my website. So anyways, let's run this and see the results in real time happening. So I've run this, and as you can see, you're seeing some random class names pop up on top. This is because obviously this is a classifier and there's a lot of things here, and obviously I'll need to make sure that the things I show to this classifier are inside those inside those 1000 classes. So that way I'll be sure that the predictions are happening properly. So anyways, and you can try this at home, and when you can show the camera an object that's inside those 1000 classes, it will probably work accurately and classify it. So anyways, this is the real-time classifier in action. When we're working with object detectors, this will be more useful, because then you will see a box around me and a labeled person here. So that will be more cool. So anyways, let me close this up. So that's it, for this particular notebook. So here are some very important details that you need to know in order to run any deep learning model. Right now you understood how the whole workflow works. But what if you have a model in mind? You already know a good deep learning model in TensorFlow and you want to use that in OpenCV. So how do you go about that? So for that, here is a overview in detail regarding how all of this works. So you can read this complete blog post here. It's called Deep Learning with OpenCV DNN Module, a comprehensive guide. And this is a blog post version of the same tutorial that I've covered right now. And like I said, I'll be covering this whole crash course, and this crash course contains 3 different parts, and this is all the first part. So anyways, scroll down below and go to the last section here, where to get pre-trained models. So this is where I tell you about where you can get the pre-trained models, and this is here's the link for it. So deep learning models in OpenCV, and you go to this page, and there are a lot of different details regarding what sort of things are supported, what layers are supported, and this is one of the most important parts. Later on I'll cover this when I'm working with the object detection model. So I'll talk about this limitation that we have at the moment, but still it's very extensive. Anyways, so you scroll down here and you'll see that some various models and zoos that you have access to. So some models are directly linked, some you have some links to the entire model zoos. So this is where you get most of the models that you'll need for your use case. And then later on, what I talk about in this talk is that where you can download those models, how you can download different models that are already tested in OpenCV. So here's a GitHub script inside OpenCV, and I talk about how you can download these models. here. So this is a script that can automatically download models if you run it, but if you just want to grab a singular model, you can also do that too. I talk about that here. And then I also talk about how to get the configuration files and the class name. So remember, for using each model, you have to have some configuration files that describes that model's architecture, and then the class names if the model is trained on a particular data set. So you need to get the class name and configuration files. So I talk about that here. And then the other thing that you do need is that you need to follow a pre-processing scheme. So remember here that I showed you that you need to do these things. Where is it? Yeah. So I showed you that you need to multiply this with this scale factor. You need to resize it to this size and subtract these values. So this is the information that I knew beforehand because the author contained, mentioned these details inside GitHub repo. So, and how to get those details is something that you need to know, and it's not always straightforward, to be honest. So for different models, you have to search properly, and there are some guidelines that you can follow to grab those details. And this is what I covered in this section: how to grab those pre-processing details and how to get those. So, and like I said, do go over this section if you're really interested in using different sorts of deep learning models inside the DNN module in OpenCV. So anyways, and there's another section where I covered how to use your own custom trained models. As I said, I'll also be covering the exact steps to do this in the next part of this crash course. So I'll be doing that, but here's just a brief description of how that works. And finally, I also talk about some backends that can speed up the DNN module. By default, the DNN modules runs on the CPU. But if you want, you can also use your NVIDIA GPU. So for that to happen, you have to install OpenCV from source. And I have this tutorial published on Bleed AI that shows you exactly how to install the OpenCV library from source with NVIDIA GPU support enabled. So this is a full-fledged tutorial on that. You can follow that if you want, but I only recommend you to follow if you have already installed OpenCV multiple times and you have experience in OpenCV. Otherwise, you'll get confused. You can also do that if you have experience installing libraries from source. So that doesn't matter there. So anyways, you can use NVIDIA's GPU, you can use OpenCL based Intel GPU if you have that one, and then you can use some other backends like the Halide backend and use OpenCV's engine backend. So there are some other options, but the most popular option and the best one is the NVIDIA GPU, and the other one I guess is the OpenCV based Intel GPU. Alright, so that's it, and there are some other points that I talk about, the maintainers of the library and some other points. As I said, some very interesting stuff that you should go over in this blog post, and it should be linked in the description of this video below. Hi, welcome to the second part of Deep Learning with OpenCV crash course. In this part, I'll show you how you can train a custom image classifier with TensorFlow and then convert that classifier into ONNX format and then use it directly inside OpenCV with its DNN module. So you'll learn the whole process and all the things that you need to know to get this whole process right on. So let's get started. So for this tutorial, I'll be working with this Jupyter notebook. Now, like always, this is a very well structured and documented notebook that will walk you through every single step and every single detail that you need to know. And this comes with a packed and detailed documented, blog post that also covers all of this that I'm going to show you in text version. So make sure to go over both of these things, and you can get them from the link in the description below. So to get the best out of this tutorial. So what you need to do first is we're gonna install all the required libraries. As I said, I'll be using TensorFlow to train the models and OpenCV to finally do predictions at the end and deploy it inside OpenCV. But I also show you how you can use it directly in TensorFlow to make predictions with the trained model. Now I'm going to start by importing the required libraries, which is, as I said, TensorFlow and primarily OpenCV. There are some helper libraries that I'll also need, like matplotlib, numpy, tar-file to unzip the data, urlib to request or download the data, and operate OS for operating system tasks. So let me run this cell. So now I have imported all the libraries. One other thing that I should tell you, that you will be working with these versions. Install OpenCV contrib Python 4.0.01 and TensorFlow version 2.0 or 2.2. I've installed 2.2 for this one. I've also created a new environment in which I'm using Python 3.6 version. So the reason for these specific versions of these libraries is because this process is somewhat, like restrictive. So a lot of times there's conflicts between, like if suppose you train a model with a particular TensorFlow version, you may not be able to use it directly in OpenCV, or you may not be able to conveniently convert it into ONNX format later on. And I'll also talk about why we are converting to this ONNX format and what is the purpose of this one. So I'll be talking about this later on, but understand this right now, that for this to work correctly, make sure to use ideally create an environment, create an Anaconda environment or create a virtual environment where you install these specific versions of OpenCV and TensorFlow. As I said, 2.0 is fine, 2.2 will also work, which is what I'm using right now, and go with Python 3.6 version. I may, I'll also add that instruction about the Python version below. It might also work with Python 3.7 or 3.8. I haven't checked it, but if you go with these specific versions, you will be guaranteed, this whole process will work for you. So anyways, without further ado, let's start. By the way, if you're not familiar with deep learning, you can follow along, but I will show you how to create a deep learning model with TensorFlow, how to train it and whatnot at the most basic level. But still, it is highly recommended that you have some theoretical understanding of what deep learning is, how it works, what neural networks are. So it will be really, really useful if you know that, what the absolute basics of it. If not, I would suggest a course in Coursera called deeplearning.ai. It's a whole specialization by Andrew Ng, deeplearning.ai specialization Coursera. You can Google that. I think, yeah, I have linked this here. So I've linked exactly, the course that you need to go over. And if you also need to learn, image processing and computer vision basics, I have a packed 3-month course here. So you can also go over that. But this course is in Urdu Hindi language. But if you're not familiar with that, I have also another course called, Master Computer Vision in 1 week, something like that. You can go over that. So anyways, without turning this into a promotional video, let's get into the tutorial itself. So now what we're going to do is I'm going to train a classifier to classify 5 different flowers. So let me show you what I mean by that. So I have these 5 different categories: daisy, tulips, rose, sunflower, and I think it's pronounced dandelions. Sorry if I'm wrong. But these are the 5 different categories. So you will be training a model on images of these flowers. Now, this is a real world data set that you will be working on. Now this data set is hosted by Google, so you will be using this link to download it. Flowerphotos.tgg is a compressed file that has zipped all these files. So what you'll do is you'll use urllib.request to download this zipped file, and then you'll unzip it using tar file.open. It's a tar file, so .extract all, open, passing the file name, and then .extract all. So by running these 2 cells, you will be able to download this zipped file and extract all of it. And after you've done that, you'll see something like this. Let me show you. So you'll see something like this. You'll see a folder here with each folder for daisy, you'll see all the images for daisy, and for every other folder you'll see images of the flower name. So you'll have this directory where you'll have all the images. So now that I've already downloaded it, so I'm not running these cells again. So now after downloading the data, the best thing that you need to do, the best thing that you can do and you should do is visualize all of the data. But before we actually see the data, let's see how many images per class we have in this directory. So here's what I'm going to do. I'm going to iterate over this directory, flower photos, and for each class name, for each folder, I'm gonna grab its full path, and then I'm gonna go inside that path, grab the total number of images, and then print it out. And then finally I'll also store the class name inside this Python list. So this will be a Python list with a string variables where each string is a class name. Dandelions, roses, sunflower, and all the 5 flowers. So let's run this. So after running this, you will see that I'll get something like this: 633 images of daisy, 898 images of dandelion, 641 images of roses. And so I've printed out all of the 5 flowers along with the total number of images inside those photos. At the end, I also printed out the classes list that I just created that consists of 5 strings. Each string is a class name. After doing that, what you will do next is you'll train a model, but there's another step that you should take, and that is that you should do data augmentation to expand that data set. So we can just train a deep learning model on these images. These are okay, but to get the performance even further, to get even better accuracy, what you can do is do data augmentation. Now, data augmentation is a really interesting and a common technique that deep learning practitioners use. Here we take an image and do some various manipulations with it to expand and create multiple copies of it. So for example, consider this motorbike image. When we do data augmentation, apply techniques on this image, we can get several instances of this same image with various transformations. So I can flip it horizontally, and I get this sort of a version. I can rotate this image and I can get this sort of a version. Then I can do some other thing and get this. Although this one looks identical, but you get the idea, right? We can rotate it, we can translate the image, we can shear it, we can distort it, and we can increase the brightness, decrease the brightness. So with a single image, we can create multiple copies of it. And this is really good because we now have a huge data set that the greater the the data, the better, the more stronger the model that we can train on. So it's good that we have a lot of data. And so this is what data augmentation does. And to do data augmentation in TensorFlow, you have this function, this class called image data generator. And to utilize this, you'll do something like this: tf.keras.preprocessing.image.dataGenerate. So this is the whole thing that you'll need to type it out. And then with this, you'll create this data generation object. And later on, you'll use this to augment the whole data. There are a lot of parameters, and I'll talk about it. But just before that, I think I forgot to mention that what is this Keras. So Keras is a high-level API over TensorFlow. So TensorFlow is a low-level library. Normally, when we're working with TensorFlow training models, we use the Keras API. Previously, I don't know if you've heard of it, but the Keras was a separate API which utilizes TensorFlow. But now it's TensorFlow 2.0. It's by default it's part of TensorFlow. So whenever you're working with TensorFlow, you'll probably be using Keras API to train the models. Anyways, you don't need to beat your head with these details, but just understand this. Keras makes your life easier when training deep learning models or creating deep learning models. And also with Keras, there are 3 specific recipes of creating models. I'll talk a bit about that later on. But yeah, I think right now it's that information alone is enough. I don't want to bombard you with unnecessary lingo. So anyways, so let's start with the most important parameters here. So once you call this image data generator class, inside this you'll pass a couple of other things. So we're going to specify what exactly or what sort of transformations do we need to apply to each image. So for example, if I need to apply rotation, I'll specify here I need to apply rotation. If I need to apply some shifting, some translation in the horizontal section, I'll specify the width shift range. And then if I need to apply some vertical shift, then I'll specify here. If I need to do some shear, something, it is sort of a distortion, so that you apply on the image, I'll specify it here. If I need to I need the image to be zoomed in or zoomed out, I'll specify here. So this is just you'll have a zoomed in view of image. You'll just resize the image, and then you'll pick a zoomed in version, or you'll pick a zoom out version, something like that. And then this is horizontal flip, either to flip it horizontally or not. So as you can see here, this is the original image, and this is the horizontally flipped version in the left side here. So this is what we're telling here. And then we also have a vertical flip. Vertical flip true. So I'm specifying both. I'm setting both to true. I'm setting it horizontal flip to true, and I'm setting vertical flip to true. Now understand this, that in there are scenarios in where you have to be careful with this. So for example, if I was training data set on motorbikes, I will not set the vertical flip equals to true, because you never see motorbikes in real life that are flipped upside down, right? So unless obviously you're taking a snapshot of a horrible accident, and that anyways, that will, let's just forget that happens and that you will need to classify when that happens. Anyways, so there are cases when you'll want to ignore vertical flip to true. You don't want to set vertical flip, and there are many cases, like many real world data sets where you don't want to set this to true, because then this will introduce data that will never appear. So this will probably confuse the model. And then there are also instances where you might want to ignore setting horizontal flip to true. And one example of that is, suppose if you're working with right hand, you're training a deep learning model to classify the right hand or do something with the right hand of the body. But if you do horizontal flip to true, then this will flip it and this will give the illustration of left hand. So, and you don't want to give the message that these are both the same, right? So there are instances where you need to be careful in those things. Now, what are these values here? The rotation range 20 means have an angle of 20 either in both directions. So similarly, we have ranges here. So which range 0.1. So there's probably a range between 0.1 and 1. So what exactly, or what sort of, if you need to know what sort of all transformations are available, what the ranges of these values are, and what these values mean, you'll need to go here. Let me show you. So you'll need to go over the documentation of tf.charask preprocessing.image data generator. So every function in TensorFlow, you can Google it and you can go to its documentation. And this is a really neat site. I haven't seen, there aren't many libraries that are good in terms of documentation as TensorFlow is. So this is really, really good. So you'll see every single transformation that you can do on the image, and this is the default values. These are all the default values. If you don't pass in anything, these are assumed that are going to be passed inside the function. And what each of these mean is explained here. And you also get the information regarding type of range or the values that you can pass inside these. So it's really extensive. So if you're more curious upon what sort of things that you can do, you can Google it and you can go to this link. I'll probably include this link inside this notebook. Anyways, so that's it. By the way, yeah, this is fill mode. This is one thing I think did not covered. Reflect. So this is just whenever you displace an image horizontally, vertically, you have a space, you have an extra space. And how to fill that space is where you specify here. So reflect. So have that part of the image reflected upon here to fill it up. The default, I think, is a constant black value. So there's that. And the other thing that I did not specify here initially was these two things. So this is the validation split. So I'm setting the validation split as 0.2, which means 20%. Now this means that I'll be using 20% of the data set to to validate it, to test it out, and the 80% of the remaining one will go for training. So I'll use 80% of the data to train the model, and then 20% to test it out on the validation set. So this is where I specify that. Finally, there's this rescale equals to 1, which is a 1 point, which is a floating value of 1, and then divide by 255. Now, by doing this, what I'm telling the data generator, I want each of the image, which is typically in the range of 0 to 255. So remember, an image contains pixels, and each pixel has a value between 0, which is black, and 255, which is white. And we have 3 channels RGB. Each of these will make any sort of a color. So we have images in the range with pixels values in range 0 to 255, but whenever we're working with training models in images, we typically try to resize rescale this 0 to 255 range into 0 to 1. And this is really useful in terms of training. It helps in training, and it gives you a better sort of a model at the end. So this is a common practice that we do to rescale all the pixels in the image in the range of 0 to 1 to make it 0 to 1. And this is how you do that. You tell it to divide every pixel value by 255. And there is also a couple of other things that other authors do, but right now we're just doing this thing, right? So now by doing this, I have created a data generation object. So I have this datagen.train. Now this is an object which I can use to transform every image in the in my data set. But here's the thing. So remember when I told you that we're only gonna use 80% of the data for the training set, and the rest of the 20% is for the validation set. So here's the thing. Whenever you are applying data augmentation transformations, you only apply it to the training set, not to the validation set. So here's what I'm doing. I'm creating two data generation objects. One is for the training, where I'm doing all sorts of these transformations, and other, which is completely an empty one, this is for the validation set. Here I'm not applying any transformations. The only thing I'm doing is telling it to rescale it, which is not a data augmentation technique. It is a pre-processing technique, and pre-processing is different. Pre-processing is sort of something that you have to do with every image that goes into the model at the training time and also at the rest time. Augmentation is something extra to increase the data set size, right? So here I'm telling the model to do this stuff also to the validation data generator, and I'm also obviously telling the data generation about the split. So I'm telling it the validation split is 20%, so make sure to have it that. So now that I have this data generation training and data gen val objects, I'll use this inside this, and I'll use this to call a function of it called data gen train dot flow from directory. Now this is a particular function that you can call on these objects, and inside these functions you can pass further details regarding where the data is present, how to read it, how to read the data, and what to do when you read the data. So just to elaborate on that, so here's what I'm telling this function. I'm telling the function, this is the directory path. So this is the directory path. See, I might have specified the directory path above. So yeah, here is it, flower photos. So this is where all these 5 folders are present. So I'm telling this, go here, you will get all the data here, and this is the batch size. So we have typically we have some sort of a batch size. I'm setting this to 60 images. So we make pass, when you train a model, you make several passes of it from the data, and in a typical pass, you get a batch of an images, you run a model of it. So anyways, that's some lingo related to deep learning. You don't need to be bothered by that, but just understand this. I tell it that you'll be using a 60 batch size. This is the path where the images are present, and shuffle equals to true, which means whenever you're loading, you need to first shuffle the data. So maybe sometimes when you're doing a train and validation split, you might want to shuffle it, because you need to make sure that all the variety of images are spread out equally. You don't need to get a particular sort of images on one end and then on the other end you have some totally different images. You need to shuffle the data. It's a good practice. So I'm doing that. Then I'm specifying a constant random seed of 40. This will help to replicate the result. Whenever I'm running this again, this will make sure that I'll get the same performance, the same metrics again and again, repeatedly when I run this experiment again. So this is why we use a random seed. And then I specify this is a training subset. This is a particular keyword which I'm using for my particular setup. You won't, and I'll talk about why I'm doing this sort of a thing later on. So, and then there is interpolation equals to bicubic, and I'm setting an interpolation method because I'm specifying a size here. So target size equals to image height and image width, which is 200 by 200. So whenever you're training deep learning models, you first have to resize all the images into a particular fixed size. I'm setting that size as 200 by 200. So this is where I'm telling the flow from directory method, that whenever you read images from this directory, make sure to resize it into 200 by 200. And the method to resize each image is this is where I'm telling it, use the bicubic method. You can use other methods like bilinear method, which is a bit faster. You might get faster speed in terms of reading the data, but it's not that accurate. So bicubic is computationally more expensive when you're resizing the image, but it gives you much better images in terms of quality. So you'll get better images. So now that I've specified all of this and I've used data gen train dot flow from directory and passed all of this, I'll do the same thing for the validation generator. So for here, I'm doing everything, all the same things that I've done here. The only difference being is that I'm setting the subset as validation. So I'm telling, this function that read the data from the same directory where you're reading a training set, but this time understand that the data that you read belongs to the subset called validation. And this sort of whole setup is somewhat, unique. People don't usually do exactly this. People, what they normally do is that they split the data into training set and into a validation set at the directory level. So here they will probably, if you go here, they will probably have 2 folders: flower photos train, flower photos valid, and inside they would have splitted the data. Now to avoid that hassle of splitting the whole data, what I'm doing here is a clever trick. So I'm telling, like I'm creating two separate data generators, and I'm, like using these subsets and constants at both, like here. And this will make sure that it reads images, and both of images, subsets are different. So train data generator, even though it's reading from the same directory, where the validation, set is present, and, like the training set is present, the directory is same, but this setup will make sure that, I get different images in the training, but when I generate images with trained data generator, and when I generate images with valid data generator. So this is sort of a unique setup. So now that I run this, I'll get something like this. You see, found 2,939 images belonging to 5 classes. Now this is for the training data generator. And for the validation data generator, I'll get this. Found 731 images belonging to 5 classes. So I'll use this data to train the model and then use this to validate it. So moving on, when you've seen the total number of images, now what I'll do now is, I'll visualize the whole thing. I'll create this function, and this will help me visualizing all the images that's being generated by this data generator. And you should do that. You should see, how good, or how is your data generator, which where you're applying all these augmentations, is making the image appear in action. So here's where I'm creating a function, display images. I'm passing it the data generator, and I'm telling it I need to generate each time this function is called 15 images, and all these 15 images will be some random images. So whenever I run this, I'll be calling this next data generator. Whenever you do next data generator, the data generator will give you some will generate random images from the dataset and provide it to you. So whenever I call this, I'll get some sample training images, and I'll get some labels. And then what I'll do is create a matplotlib plot, and with that plot, I'll create some columns and rows. I'll get the total number of samples here, and then I'll plot each sample out in some rows in 5 columns. So how many total rows I need is determined by number of samples I'm trying to display. And so this is the total syntax to display some images. So I've initialized this function. Now I'll call it using the valid data generator, and then I'll show it to you using the trained data generator. So let's run this, and you'll see this. So these are some images that has been read with the valid data generator. And yeah, so this is how this looks like: daisy, sunflower, 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 dandelion, daisy, tulips. So it's randomly being picked up from the directory and being displayed here by the valid data generator. So if I run this again, you'll see a different sort of a set. So see this, the sunflowers, tulip, daisy, sunflowers. So this is a different batch which it picked up and generated for you. So you can see all these 15 images. You can increase this number to visualize more images at a time. And then I'll just try to display it with the trained data generator. This time you'll see some distortions because data augmentation is being applied. So as you see, you can clearly see that this is where vertical flip is being applied here. And this is probably where I think horizontal flip is being applied. Again, vertical flip, I think. Then you'll see some other distortions, some resizing, zooming. Right now, I'm not applying any serious augmentations because you're seeing I kept the range really small. I only told to shift the range with 0.1, 0.1. So I'm not applying any serious augmentations. You can experiment with this to create a more diverse data set. So anyways, so here's how you can visualize the data, and it's really important that you always do that whenever you try to augment novel data that you haven't seen before, and maybe you don't have any idea how this looks after applying these sort of transformations. Make sure to visualize it so you know at your end the data set looks good. Now that we have finalized and downloaded, sorted, and created the data sets and the data generators, it's time to create the deep learning model. But before that, now this is where I'm creating the model. But before that, see these two lines. This is where I'm resetting the validation and the trained data generators. And this is really important because whenever you generate these images, those images have been generated. They won't be generated again. So you need to reset it because Later on, when we train the model, we'll pass in these generators, and they will be expected to generate images fresh, right? You like for the expected to generate images first time. So you should reset these. So yeah. Now I'm gonna just run this. Now I'm gonna explain you like what's happening inside this, how I'm creating a deep learning model with just these lines of code. So this is what's called a sequential API. Inside Keras, you have three options exactly. There's a sequential API, and for creating more complex models, you have functional API, and then creating even more complex models, you have a subclassing API. So for this particular tutorial, I'll just be dealing with the sequential API, and you can create many like different models, and that stacks layers upon layers with each other with this sort of an API. So if you're training models, like that have layer upon layers, sequential API is the go-to API for this sort of a model. So yeah, so this is what we have. And just to go over like this structure, before I talk about this, let me show you a simple example, a simple illustration of how this looks like. So see this. So I have like something like this. Now this is an example of how a deep neural network looks like, a convolutional neural network looks like. So here we have an input image, and inside this input image, like we apply some convolutional layers, and inside convolutional layers we have some filters, and after those filters go over the image, like this box here is a typical like a filter, a convolution filters. It goes over an image patch, it does some calculations, and it provides you an output, and then you use that output to create feature maps. And so you have multiple like convolution layers. This is one layer, then this is another layer. So we have two convolution layers here, and inside each convolution layer you have multiple filters. So for example, you take this 28 by 28 input, you apply a number of filters over it, and then you get this sort of stacked feature maps. And then you apply max pooling operations. Max pooling operations divides like a typical max pooling operations of 2 by 2 divides the whole image in half. So when you do that, you get all the feature maps in half, and then after that typically you also do other convolution operations, and then after doing that you get even more stacked feature maps, and you repeat this process multiple times inside a typical deep learning network. And at the end, what you do, you take all the feature maps and you flatten it out. You flatten it out into a single like array. So this is where we call it like a flattened layer. We use a typical flattened layer to do this, and after that we have a dense layer or a fully connected layer. So we have something like this. If you have used like dense networks, which is the other type of popular like architecture in deep learning, a deep dense network which contains multiple fully layers, we have nodes like this. So this is different from a convolutional neural network. Again, I'm sort of assuming that maybe a bit about this jargon, what convolutional networks are. Even if you don't, just try to understand here that we have multiple convolutional layers. Each convolution layer is followed by a pooling layer to reduce the image size. And inside each convolution layer, there is something called filters. Each filter generates one feature map. So if you have 5 filters, you'll get 5 feature maps output. So this is how this whole workflow goes. Throughout the network, as you go forwards, you'll see that the feature maps grow smaller and smaller because you have more and more pooling layers being applied to them, and every pooling layer is halving the size of the feature maps. And as you go forwards, you also see the feature maps increase because you typically increase the number of filters inside each convolution layer. And you'll see this when I'm showing you the architecture. At the end of the layer, you have this outputs. So if we were solving a number classification problem, we wanted to classify if the number is 0, 1, 2, 3, 4, 5 all the way to 9, then we will have 10 output nodes. Each node will classify a single class. So 0 will if the output is 0, you'll know it's a class 0. So 1, 2, 3, similarly you'll have these output nodes. But before this output node and in between this flattened layer, there's another layer called fully connected layer, and this is important because at the end all the flattened outputs will go to this dense layer, and it will do the final computation. And then the final computation will go to the outputs and tell you what sort of prediction the model thinks the image has. So this is a typical flow, and yeah. So whatever I've just said, I can show it to you. Like something like that. So as you see here, we have like convolution layer here, and followed by a pooling layer. Then we have another convolution layer, followed by pooling layer, another convolution layer, followed by pooling layer, another convolution, pooling, convolution, pooling. So we have done this 1, 2, 3, 4, 5 times. In this image, you see this is happening like one time, and this is like pooling operation, and another time pooling. So this is happening only 2 times here, and here it's happening 5 times, right? And at each time you'll see this is the number of filters. So initially I do 16 filters, then I do 32 filters, I double it, and then I do 64 filters, I double it again, then I double it again, and then I double it again. So each time, and this is a common practice, you double the number of filters, and this is the filter size. So here I'm using kernel and filter size of 3 by 3. So by specifying here 3, I mean 3 by 3. I can also do something, you know, like 3 by 3. This will also mean the same thing, but this is a shorthand for this. So 3 by 3 filter, but in this graph you'll see that we are applying a 5 by 5 kernel. Kernel is also another name for a filter. So 5x5 means we're applying a 5 by 5 box, making the box go over all the image, do the computation, give you the output. But instead of a 5 by 5, I'm using a 3 by 3. So 3 by 3 all the way for 5 different you know, like layer sets. In each layer set you'll see that I'm also, you know, like doing max pooling 2D. And by default, I'm using all the default parameters. By default, you half the size. You use a 2 by 2 kernel, and this will make sure, you know, like you half the image, the input, the filter input. So you'll get you know, like you'll get half the size. So why don't I just, you know, like show you this, how this looks like. So let me run this, compile the model, and get back to this and give you the summary of how this looks like. So you see, we started the image with 200 by 200. Remember, we resized all the images into 200 by 200. So that's why this comes from 200 by 200. And we took, you know, like, I think we passed the batch as 16 in 200 by 203. So yeah, 16 filters. We did 16 filters. This is where this 16 is coming from. And in total, it equated to 48 parameters. So then what we did is we applied a pooling layer, and this reduced the size in half. Still 16 filters here. And then we did dropout. I'll explain about this. And then we applied another convolution layer, and this you know, like doubled the filters. 16 became 18. Similarly, as we're applying more convolution filters, we're doubling this filter size. 32 became 64, 64 became 128, and all the way to 256. Similarly, we are halving the size each time a pooling layer is being applied. 200 turns to 100, turns to 50, turns to 25, turns to 12, and then turns to 6. Each time we're keeping sort of a balance. When we're increasing the filter size, we're reducing the image size. And this is really important because this way you control the number of parameters. Because the greater the number of parameters, the chance that you overfit the model. You know, like when you overfit, it's a bad thing. I'll just leave it at that. And you increase the size of the model, which is unnecessary when you can get back at accuracy at a lesser size or a reduced size. So this is what we typically do. Alright, so one other layer that I skipped about was this dropout layer. Now, dropout layer is a regularization technique which tries to control the performance of the model. It controls the overfitting. When I say dropout equals to, you know, like brackets 0.10, this means 10%. Dropout 10% of the parameters when I do this, and it will randomly drop out any 10% of the parameters, and this will help in improving the overall performance, because whenever 100 people come to you and you randomly drop out the output of 10 people, everyone will know that, you know, like even if they're relying on certain key people like 5 to 10, if they were dropped out, what will happen to the collective output of the whole team, 100 team, right? So everyone will give their best. So this is a good technique, a regularization technique to control the output of the model. So we can, you know, like do dropout at here, 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 and here. So you can apply it. I just applied a dropout layer at here. So it's your choice. All of this is a really basic architecture. You take this, you can experiment with it. But it's important that you at least understand the theoretical foundations of deep learning, then experiment with it. Otherwise, you'll just be fooling around with the network, because there's a lot of intuition of the different decisions that we make. For example, padding, I kept the padding equals to same, which, you know, like keeps the output size of after convolution operations applied the same, and there's an intuition behind that. I'm applying activation of ReLU. Why I'm doing ReLU, which is a very popular activation, why it performs best. There's a theoretical intuition behind that. So every single thing being applied. It's really, really intuitive and it's beautiful once you understand how this all works. After all of this, at the end, what I'm doing, I'm flattening the layer. Now there is a layer called flatten in TensorFlow.keras. You can call that to flatten the layer, but there's an alternative technique called global average pooling, and this is much better than flattening because it averages all the outputs of the last speech map, and this tremendously reduces the number of parameters. So this is really, really neat and much more useful than the flattened layer in deep learning in TensorFlow. So use that instead of flatten layer for this typical scenario. After that, when we have done the flattening, I'm calling this dense output layer, setting it to 1024 parameters, and activation is ReLU. So this is the fully connected dense layer that I told you that comes between the global average pooling and this dense layer. And let me just comment this one out. I don't think this one should be there. Okay, so then what I do is that I take the length of all the classes and I set the final output layer to that, because the total number of classes is the total number of output nodes that I want. If I am classifying between 5 different flowers, this should be 5. If I add a new flower by adding a folder with images of that flower, I'll have to increase this to 6. So I'll just do length equals to classes. So this way it automatically updates because right now the classes list has 5 strings, so the length will be 5. So this will work. And the activation is softmax, and this is the most common final activation that you use for the output layer. This will make sure you get the right sort of get the probabilities out at the end. So anyways, this is how you create a sort of a typical deep learning network. So I hope that you get the brief intuitions that I provided for each layer. There's some details that you can also read here and maybe learn more about it. Then you can also go to these links to study more about these specific layers, what they do, why they're useful. Anyways, after you've done creating the model, you'll have to compile the model. So this is where this comes in, model.compile. You'll call this .compile function. Inside this, you'll pass a couple of other things. So I'm gonna set the optimizer. So I'm using an optimizer called Adam. This is the most common optimizer. This is the algorithm that will make sure the model learns from the data. It optimizes. It's the whole algorithm that manages the training process. And then inside it, you specify the learning rate. Now this is a typical learning rate, 0.001. You can if you increase add another 0, the learning will slow down by 1/10. But if you decrease a 0, the learning will speed up by 1/10, but by 100%. But it will be very risky. It can underfit, something like that can happen. And again, there's whole intuition of what sort of a learning rate you should use. But this is a very common learning rate for this sort of a scenario, and it will work fine. Then as a loss, what sort of thing that we're monitoring? So for example, if we're training a deep learning, how would we know that it's doing good? We specify loss. That's something that should decrease. So for this particular scenario, we're going to use a categorical cross entropy. So categorical cross entropy is a loss that you use when you have a multi-class classification problem. So we have a multi-class classification problem because we have multiple classes, like more than 2, 3, 4, 5. We have 5 classes, and we're looking to classify them. So this is where we use categorical cross entropy. And finally, optionally, we're telling the model that the metrics that I'm most interested in is the accuracy. I'm interested in how accurate the model gets over time when it's training. So this is where we do this. Finally, at the end, we print out the model summary, and this is where we studied earlier. This is the whole description of the model, how many layers it has, how many parameters each layer has, total number of parameters, trainable parameters, non-trainable parameters, and whatnot. There's also another function that you can call. It's called model plot, something like that, and it will plot out the whole structure, so you can visualize it, even matter how the whole model looks like. But this is a really simple model. It's just stacked few layers. So you can understand everything about it by just looking at this. Now that we have compiled the model, it's trying to train it. By the way, I think I skipped upon this. This is just a callback. This will make sure the model stops training when it reaches a reasonable accuracy. Not accuracy to be precise, but it's monitoring something called validation loss. When the validation loss goes, most probably the overall accuracy will increase. So and just to briefly explain this will stop the model from training further when we reach our desired results. So yeah, and after that, what we're doing is that we're training the model. This is where the whole training starts. So I'm specifying epochs equals to 30. This means the model will look at the whole data 30 times. After 30 times, the 30 epochs will be up. So, and to finally start training, what you'll do is model.fit, you call the .fit method. You'll pass in the train data generator, and then you also pass in, like the validation data generator. Where is it? You'll pass in the epochs, you'll pass in the, yeah, here's it. You'll pass in the validation data equals to validation data generator. This will, you'll pass in both the data generators. You'll also pass in the number of epochs, and then I'm also going to set the callback. So this is where you specify, use the early stopping callback. Again, it's optional. And then we also have two other things, steps per epoch for the training data generator, and steps per epoch, I think validation steps. This is where I call this. Now, whenever you're training a model, it works on batches of data. So you have to set this number equals to, how many batches you need to go over to complete the whole data, completely go over the whole data set. So this is where, we're doing a simple math to calculate how many batches, considering the batch size is 60 and the whole data set size is, I think I'll have to look it up. And so the whole data set is this, and the batch size is, like this. So divide this by that, and how many epochs I need to, how many steps I need to take to complete a full epoch. So this is where, you do that. Anyways, once you're done, you can start the training. So I'll just, turn this on, and it will start the training process, and you'll see, estimated, time here, the seconds will decrease when it reaches 0. It will complete an epoch. And here you're seeing 48 is total number of steps, training steps that's being happened. Like at each step here, it's going over a batch size. So when it reaches 48, it will have gone over the whole data set, and it will repeat this whole process again. So right now I've already trained this model, so I'm going to stop this. So this gives me an error because obviously I stopped in mid training. So yeah. But I have already, trained this whole model, so I don't need to worry about that. And I trained this model for like 30 epochs, and I should have trained it for 60 epochs. So the model that I have trained just now is not the best performing model I should get by this configuration. I should get even better results if I had trained for like 60 epochs. So ideally you should go for 60 epochs, but I'm just running this model on CPU. I didn't bother setting up this with TensorFlow GPU, and if you have a GPU, and I do have it, I have a strong one, but I didn't bother to configure it and run it on that GPU. I just ran the example on this CPU. But if you have that and you have already made the configuration, be sure to run it on GPU. And the other reason I didn't run it on GPU, I needed to make sure that this setup works fine with everyone. Everyone has a CPU, but they don't necessarily possess a good NVIDIA GPU, right? So you can get good results with training this on a CPU by just 1 hour, 1 or 2 hours. That's it. So yeah, so this is a good testing data set. So anyways, now that we have trained this model, as I said, I've already trained it prior to recording this video. So I'm going to visualize the results, and to do this visualization, I'm going to use this history object. Whenever you do training, you store all the information regarding the metrics, the evolving metrics, in this history variable. And then what we do is that we do this history.history. We extract the accuracy, we extract the validation accuracy loss, validation loss, we store these variables, and then we plot it out. And it looks something like this. So this is a chart which shows you how the training accuracy evolved over a total of 30 epochs, and how the training loss evolved over a total of 30 epochs. And this looks sort of good. I mean, it's not perfect, but it's really good. As you see, the accuracy increases, both validation testing, there's no overfitting or underfitting going on. So again, here you see both the training loss and the validation loss decreases over time, over the 30 epochs, and it was continuously decreasing. So I would have gotten better accuracy loss given I had trained it for more epochs. So now that we can clearly see that we have a good model on hand, let's test it out. So for testing, I'm going to read an image with OpenCV cv2.imread images rows.jpg. Now this image was not present in the training set. So I'm reading this image and I'm then in OpenCV, the image will be read in this variable, and then I'm going to resize the image to 200 by 200, and I'm going to convert. So remember, before training we resized all the images by 200 by 200. So you have to do all of the things that you did before training, all the pre-processing steps before training, whenever you're trying to predict on new images. So you have to repeat them, and you have to make sure that both that you don't make any like mistakes here. So I resize the image to 200 by 200, and then I convert it into RGB. And this is important because in TensorFlow you train images in RGB. So TensorFlow normally works with images in RGB, but OpenCV reads an image in BGR, which is the reverse of RGB, right? So you have to convert the channels, reverse it. You have to like convert BGR images into RGB. So this is where we convert the image into RGB. And finally, one final thing that we do is that we divide the whole image by 255, because remember, we initially when we trained the model, we divided all the images, converted from 250 0 to 255 to 0 to 1. This is the same thing that we need to repeat. Also, I'm also enclosing this into another array because TensorFlow expects an image in 4-dimensional, and whenever you read an image in OpenCV, you have a default image in like 3-dimensional, like RGB, and then you have width and height. So you attach an extra channel, you array and enclose it, enclose an image inside it, and then you get this final format image which has all the pre-processing steps done. And then you take this final formatted image, pass it in this model.predict function like this, and then you get this predictions out of it. Now this predictions variable where you have the output, and you'll now need to extract this output. So this is how you do that. You do np.argmax, which will give you the index of the class which has the highest probability. And this index, if you have 5 classes, this index will be either 0, 1, 2, 3 or 4, something like that. And then you do np.max to get the highest probability. I mean, for example, if this was a rows, like this was a rows, now rows might have gotten like 70% accuracy for this particular image. So you'll be getting the probability, the exact value which this index class achieved. Now we'll use this index inside this classes list, and we'll get the exact label. So suppose I go above and I see this, here is the classes list. So the classes list, yeah. So see this. We have this classes list, which is a list of strings. We have daisy, dandelion, roses, and flowers to list. So suppose I'm using a rose image. So I will have gotten the index of 0, 1, 2. The index would be 2. Now if I insert this index value inside and extract the value at 2 index in this list, I'll get roses. So this is exactly what I'm doing here. I'm using this list which I created above, passing it in the index of 0 and getting like the label, passing it in the index of 2 and getting the label, which is going to be rows, hopefully, because if the prediction is done correctly. And then I'm printing out the whole results and showing you the exact image which I've just tried above. So as you see, the confidence is 89.18%. The model is really confident that this is a rose, and indeed it is a rose. So we have done the whole training perfectly. So give yourself a pat if this was your first time training a deep learning model. So even like we haven't discussed how to load this model, convert it into ONNX, use it in OpenCV, but even before that we have done a lot. We have trained a whole model, a whole deep learning model, a whole deep learning classifier inside TensorFlow. We have understood what different metrics are, how to construct the model, what different things mean, and how to finally use the prediction model at the end. Now, one final thing that you need to do at the end is you need to save the model. So you can easily do that by calling model.save, and you can save it in this directory, model directory, and I'll call it flowers1.h5. H5 is the popular format for Keras. So this is the default, I think the most common format that you save the models in. So model.save, model flowers1.h5, this is what I'm calling it, and I'm saving it. Once you run this, you'll see that you have a saved model here. So let me show you. You'll have, see flowers1.h5. This is the model that you have just saved here. So this is what you can do, And let me just run this again. Yeah. So anyways, yeah. So this is the whole process of training a deep learning model and saving it in disk. Now let's go over the part 2. Now this is part 2. This is where we take our .h5 TensorFlow model and convert it into ONNX format. And here's the reason we do that. Basically, OpenCV does not directly work with .h5 models, meaning you can't take a .h5 model, plug it in OpenCV and use it. You need to have a different sort of a format. And previously we used .pv TensorFlow formats, but with TensorFlow 2.0, that became a bit difficult, and there's no convenient way to, easy way to convert those models in .pv frozen formats and use it in Keras. There is always, I've tried that, there is a bunch of errors that I get, and the process is not as simple as it should be. But I believe that in future OpenCV developers will make it more convenient to use either a safe model format or .pv format with the latest TensorFlow version, the latest OpenCV version. So hopefully this process will get more convenient, but at this moment you'll have to use this intermediary ONNX format, which is okay. But again, it's an intermediate step that you have to do, but it's really simple. It's just 2 to 3 lines of code that you need to do. So, and by the way, if you weren't familiar with ONNX, this is a great introduction for you, because ONNX is a great format to train one model in one framework and then use it in another one. For example, you can train a model in TensorFlow and use it in PyTorch, or vice versa. Now, this image clearly outlines what you can do with ONNX. You can take format in one popular framework, train it, and deploy it in another one. And so this is the ONNX OpenX Neural Network Exchange format. This is the full form, and again, the whole thing is explained here. If you need to study more about it, there's a good link which goes into ONNX GitHub repo, and there's more information about it, what limitations it has, like what sort of thing you can clearly do with it. But the whole gist of it is that it's an intermediary format which you can convert with one to another one. So to get up and running with this, all you need to do is pip install Keras to ONNX and pip install ONNX. So this Keras to ONNX will convert the keras.hy file into ONNX, and this ONNX module will be able to save that ONNX file in your directory. So, but when you install this, I think by default this will also be installed. So yeah, you can do both of these. You can install both of these libraries, and after you've done with that, make sure to import ONNX, import Keras to ONNX, and then load up the model, and then let me just run this. So you'll see something like this: TF executing mode true. You go to the ONNX operator. So these are just some warnings. Ignore that. But if you go to your directory, you'll see that there is a file called flowers model1.onnx present there. Now you can use that ONNX module. By the way, you can also directly use it with ONNX runtime. You can install this and you can use it with this. So you don't even need to use OpenCV. You can train a model with TensorFlow and use it directly with ONNX if you want. But the whole purpose of this tutorial is to train a model with TensorFlow and then directly use it with OpenCV. So now what we're going to learn is that how to use this .onnx file, which we've just created and included in our directory, and use it in OpenCV. One major advantage that I should mention is that this sort of a thing, the model when you convert it into ONNX, you also tremendously reduce the model size. So you can reduce it by like 1/3, I think. So if you have a model with 7.5 MB, and you can reduce it to like 2.5 MB, something like that. So this is also really handy if you're trying to reduce the model size. So now that we have done that, now let's use it in OpenCV, and this is the part 3 of this tutorial, and this is the most fun part. You finally use the model directly in OpenCV that you just trained with custom data. So let's run the imports, and I think I've already run this, but when running this, you'll see, let me just go above, you'll see the OpenCV version is 4.0.0, and this is important. You'll need to have this exact version of OpenCV. This is not the latest version, but this is the version which will work with this. Now, I haven't tested with the most latest version of OpenCV, but I've seen, as I said, conflicts of this happening with 4.2 and 4.3. Maybe these conflicts were fixed in the later versions, but I have not tested this. Now, these are the versions which I have tested this tutorial with. So you're free to test it out with the later versions, but I don't, I can't guarantee that those will work. So anyways, Once I've done that, I'll just create this label names list: daisy, dandelion, rose, sunflower, tulip. So I'm just creating this whole process again. So even if you don't run everything above, you can just run this below and it will work fine. So importing the libraries, storing all the names in the Python list, sorting the list, and this is important because when you're working with TensorFlow, you train a model on a bunch of classes. The classes will be sorted in alphabetical order. So this is the same thing that you have to do again in OpenCV. So you do labels name dot sort. So this will make sure that all the things are sorted in alphabetical order. So this way, when you put the index and grab the label of that index, you'll get the correct value. Otherwise, you can mess it up. So after sorting this list, you'll just read up the deep learning model by doing this: cv2.dnn.readnet from ONNX. You'll pass in the directory and you'll pass in this model, and then after running this, you'll need the entire model in net. Now, oftentimes, if you did not, if the version has, if you read a different version of OpenCV and it's not supported, you'll see an error in this line. And this is the line which will tell you if your model will work correctly or not. So if this loads up fine, then you're all set to go. So after loading up the deep learning model in this .NET object, what you do is just you read up an image, you do all the same things that you did above when working with TensorFlow. The only difference will be the prediction part. So you read the image, you resize it with 200 by 200, you convert the model from BGR to RGB, and then you again pack it with the array, you divide it by 255. And then remember this part, when you're working with the DNN module, all of this is the pre-processing step, and this was done with Blob from image function. You can also use that instead of these 3 lines if you want, and that will work fine. So with Blob from image, you can use that, and in fact, this might be a good exercise for you. Replace these 3 lines by using a single line Blob from image, and use these pre-processing operations inside that line. So this is a good exercise. After that, you have to pass that blob inside here. So now this is not an image, this is a blob, like in OpenCV DNN blob, which we created in the first part of this crash course. Insert this blob or modified image in the net sort input. Now the deep learning model, you have set the input. After that, you just do this forward pass net.forward, as we learned in the first part of this crash course. You get the predictions here, in this out variable, and then you do the same thing that you did above. You grab the index, you grab the probability, and then you grab the label by using this index, and then you just create a text, predicted this class, the probability of this class is that, and then you just use cv.output text to finally put the prediction text on top of the image. You display the results with matplotlib. So that's all there is to it. Let's run this and see the fruits of our work in action, and this is it. I think I should clap it right now. I know this is for me and maybe for you too. So because I remember when I was doing this the first time, when I was creating this tutorial a year back, when I wrote this blog post initially. So I haven't seen any tutorial, anyone done this thing. So and I did face a lot of errors when I'm working with, and mostly these were related to different versions, and the whole process wasn't documented properly in the GitHub repos, in the original GitHub repos, and it was somewhat troublesome. And then later on, in the final part of this tutorial, where I'm going to show you exactly how to train a custom object detector with TensorFlow object detection API and use it in OpenCV DNN module. It was also a bit hectic to get that right because of version conflicts, and I ended up using TensorFlow 1.0 to make that work. So this was really cool and gratifying when I finally got this to work a year back. So yeah, that's it. One other thing that I always do at the end is that I wrap up all of this code inside some functions. So I have this initialization function where I do all the initializations, where I read the classes, sort it out, read the model. This is something I do only you do once, and then I create this classify flower function, where I take all of the pre-processing code and all the post-processing code, put it inside, put the prediction line here, and then I return the data whenever I'm working with videos, or display it whenever I'm working with Matplotlib. Now this is a very common workflow that if you have read my blog post, I do every time I've explained everything line by line. I just wrap it up in modular functions and run them, initialize function, and then I test it out in a couple of images to make sure that it works across a different variety of images. So this is where I'm doing that. Let me run this. and you'll see everything in action. Predicted deadline 55. I think this is a sunflower. This is wrong. This is a false prediction. But as you can see, you can get wrong. By the way, when I was testing this initially, I didn't get a single example wrong. I think I trained it again, and for some reason it didn't predict it correctly. So that's incorrect. That's a tulip. That's right. That's, I think that's a dandelion. That's a daisy. That's right. So overall, it's really good, and you can, as I said, you can improve this a lot by just like going over more epochs, or maybe like messing around with the parameters of the neural network here, the architecture. Or but as a first experiment, you have to increase the number of epochs. You have to let it train on multiple epochs, and this way you'll get a good accuracy. Some things that I should mention at the end that you should be careful about. One is the version conflict, that you should know that there can be version conflicts, and there's 2 points of failure in this whole pipeline. The one point is when you're using the keras to ONNX function. You can have version conflicts here. The other point is when you're using that ONNX module inside directly in OpenCV in the DNN line. So this is where you can get, those two are the things which way you can get errors if you use different versions. So if you're trying to use the latest version of a particular library, make sure be aware that you can face issues due to various like supporting layers in different libraries with regards to the other library. So there can be a lot of issues in that regard. So, and the other thing, right now I've just trained a simple convolutional model, but if you try to create a more complex model using a functional API, like with multiple heads and whatnot, you can get conflicts. So if in order to avoid that, you should go over to like the ONNX part and the DNN part and see which layer types are supported. And this is some advanced stuff. If you're trying to train a very complex model with a sort of a different complex architecture, you need to make sure that the layers that you're trying to use are supported by ONNX and are also supported by OpenCV's DNN module. So if both are supported, then most likely that would work. But that's something that you should check it out because like you don't want to be the guy that trains a whole complex model with the intention of using it in OpenCV and later on learns you can't use it because there's the particular layer is not supported in OpenCV. And there's a whole GitHub repo. If you have watched the first part of this crash course, I showed a full documentation of OpenCV's DNN library where we have sections dedicated to DNN supported layers, what type of layers are supported and whatnot. So there's a whole description. So make sure to read. This is the second part. Make sure to go over this first part. I've discussed a lot of things regarding this in detail here. So anyways, this was the first part that we did. Now this is the second part, and finally we have completed this second part. And now not only you know how to use the DNN module effectively, you also know how to train a custom model in TensorFlow and directly use it in OpenCV. And this is really powerful. Hi, welcome to the final parts of this course, where I will teach you in a very detailed step-by-step manner how to train your own custom object detection model using TFOD API and then deploy it directly with OpenCV's DNN module. In between the whole pipeline, I'll be showing you various techniques, tips, and even some things like how to annotate your data, how to download any YouTube video and automatically create a data set out of it. So we'll be discussing a lot of extra useful stuff along the way that will help you when you trip off. And I'll also be showing you how to do the whole process in a Windows PC and in also a Colab ready to run Colab notebook. So even if you don't want to be bothered with all the installation and setup, you're all set to go. So there are 3 things that you will get when you follow along with this tutorial. So let me bring this up here. So we have 3 things here. So this is a very well detailed blog post that I published a year back about the whole procedure that I'll be covering in this tutorial. So make sure to go over this blog post to get the most out of this tutorial. And the other thing that I'm going to be sharing is this Jupyter notebook. Again, this is a very documented, very detailed documented notebook that covers every single steps, and it also covers some warnings that you should avoid and things that you should need and also some tips. So this is the whole notebook that, like it's very extensive, but I'll be explaining everything in a detailed manner. And the third thing, which is, like the best thing that you will get when you're following along with this tutorial, is this collab notebook. So this is a ready to run collab notebook. Everything is pre-configured. All you need to do is just run the cells. Obviously, I'll be explaining each and every single step, so you get the idea what's happening. Like you don't just need to run the cells. So I'll be explaining, like in the most detailed manner what's happening and why it's happening and whatnot. So anyways, there's that. So these are the three resources that you will be getting when you download the full code for this course from the link in the description below. So now that's out of the way, let's get started. Before I dive into the code, let me go over the whole workflow that we'll be following along. So this, like image summarizes the whole workflow in a very brief manner. So we'll start by, like downloading a YouTube video, any YouTube video which you can get a link to. We'll create a Python script that can, split the video into multiple image frames. We'll use the image frames and, use an annotation tool like labelImg to draw bounding boxes around the objects. With that, we can get the .xml annotation files. So this is the particular format in which we will store the bounding box coordinates for each detected object, for each object that we want to detect inside each image frame. And then we'll pass these .xml files and these image frames into a TFrecord generator, which will generate TFrecords. Now this is the same data, but in a specific format. I'll be going over later on what's exactly, like this means and why we're doing that. After we have the data in the required format, TFrecords, we'll be training a deep learning model on this data. After we're done, we'll get a final trained model in .ckpt or .checkpoint format. Then we can also use this checkpoint format to make predictions, but it's better to get a frozen graph out of this particular format. So we'll use another script called frozen graph generator, which will generate a frozen graph model. So this is this is the same model but in a different format. Now we can also use this model to make predictions in TensorFlow, but remember the end goal is to use this model directly in OpenCV. So for that, we will use this graph to generate another file called graph.pbtxt. And when this file is generated, we can now use both of these files, the frozen inference graph and the graph.pbtxt, to finally use the deep learning model directly inside OpenCV. So this is the whole workflow. Obviously, there are intermediate steps or in-between steps involved along the way. I'll be explaining them when I'm going over that. All right. So, there are a bunch of other things that we'll be covering. This summarizes that. And as I said, to completely, get the most out of this, make sure you have watched the previous two parts or previous two sections of this whole 3-part course, right? Or series. So before, we start with the code, let me just briefly recap what TensorFlow Object Detection API is. So here's the GitHub link of the, So this is the link of the TFOD API, and we have TFOD API, the latest version, TFOD API version 2, and this is the version 1. And in summary, what it is, it's just, consider it as a high-level wrapper over TensorFlow that makes it easy to train object detection models. So obviously we will not be training the object detection model from scratch. We'll be doing something called transfer learning, where we will take a pre-trained model that is already trained on a particular dataset. Normally it will be a COCO dataset. So for images, the most popular one I think is ImageNet, and for object detection task we have Pascal, but the COCO dataset is a really popular one. So it has 90 classes. So, but obviously we are not interested in those 90 classes. We are interested in creating our own custom object detection model, but we don't start necessarily from scratch. And this is all something that you learn when you go over deep learning theory, which is not the goal for this tutorial. So I'm going to assume that just understand, that we do something called transfer learning, and it makes the whole process a lot faster and easier and more robust. So this is just a high level library over TensorFlow that makes it easy for you to train TensorFlow Object Detection API. In fact, you don't even need to code. So the main intention of this API wrapper is that you don't bother yourself with code, because when you're talking about object detection models, every year we we were given a bunch of new state-of-the-art detection models that has very complex architectures. And if you try to write them from scratch, you will mess up. So it's not a good thing that you should write object detection models from scratch unless you're a hardcore researcher and that is your goal, to create models from scratch. Because as I said, if you're interested in training object detection models with the best accuracy, the best metrics for solving a real world problem, this is the way to go about it. Use these libraries and and understand the theory behind it. So this is the best thing that you can do. Understand what different parameters mean, what they do, how you can tune when the model doesn't perform, what changes you can make. This is the thing that you need to learn to get the best out of this. So I can teach about this API to you all day. So I have studied a lot, I've done a bunch of things with this, but for the sake of this tutorial I'm gonna keep this really short, but even that itself will be a big tutorial. So let's start with that. But yeah, one other thing, I'll be using the TensorFlow Object Detection API version 1 instead of the version 2 for this particular tutorial, and there's a reason for that. You can go over that reason by reading this. So this is the whole reason, and just to summarize this, version 2 does not works nicely with frozen graphs, and we need frozen graphs to use it inside OpenCV's DNN module. We can theoretically generate frozen graphs with version 2, but it's a lot hectic, and it's a lot incompatible in multiple cases. So anyways, I'll leave it at that and I'll start with the code. So as I said, we have two notebook files. One is the collab one and the other one is the local one that you can run on your PC. Now I'm going to be following along with this collab node for multiple reasons. For one, I don't want to configure my system to work with TF1 GPU. I already have it for TF2 GPU. I don't want to get the CUDA and QD and write versions to make it work with TF1 in my PC. I don't want to bother myself with that setup. I'm just gonna test it out. I have done the training in my PC a while back, I think a year back. But for this tutorial, right now I'm just not gonna bother to do it again on this setup. This is a different setup that I was using a year back. So anyways, so you can do both of these. So the only difference is this step. So part one, the environment setup, and there's one or two minor differences in when you're installing the TFOD API, and I'll just show you. And those are optional steps, anyways. So let me briefly go over the environmental setup if you're interested in running this locally on your PC in case you have a nice NVIDIA GPU that you want to utilize. So this is what you do. Make sure to install TensorFlow 1.15, and then most likely you will create a Anaconda environment like this TFOD API version 1. When I was testing, I used Python 3.7, but it works with the latest versions too. But when running this locally, I initially tested this with 3.7. So yeah, so after you've created this environment, make sure to install the TF version 1.15, and then install a Jupyter notebook inside that environment, and then make the other necessary installs like install YouTube DLL, install TensorFlow and PAFI. This is for downloading video. By the way, there's one minor change I think I forgot to add, is that instead of adding this PAFI, add this one. I think I'll probably be making saving this later on. So there wasn't a particular issue with the when YouTube introduced the disabled dislike option too. Anyways, so what you need to do is just, now this is the only step that you need. Create the environment, install TFOD API version 1, and if you want to use your GPU, I've already also published a tutorial exactly on how to leverage your TensorFlow GPU and make it work on Windows PC. So there's a nice tutorial on that published on Bleed AI. So you can follow along with this one to make it your GPU work with the Windows PC. So anyways, let's start with the actual code inside this collab notebook. As I said, it would be really great if while you're watching this video, make sure to open your collab on the side, and follow along, because as I said, you don't need to install or configure anything. Just run the cells and understand the theory or the reasons as I explained to you. So so here are all the necessary installs we're installing. As I said, TensorFlow, PAFI, labelImg. This is a annotation tool. OpenCV control Python. This is the OpenCV library that we're going to be using, and yeah, that's it. these are all the installations that you need to do. Once you run this, all the like installations would be done. And I'm just audit. Also make sure that you're running a GPU. So I think I'm just gonna check. Is it runtime? Change runtime type. So we are running a GPU, so that's all good. And I'm just gonna run this. I think I have already installed. This would not take much time. And if it's taking time, obviously I'll be cutting those parts of the video. Alright, so I paused the video, and now all the installations are done. I think, yeah, the notebook resetted because like I tested this whole thing yesterday. So anyways, right now all the installations are done, and when you scroll down below, there will be a couple of warnings, just ignore that. And yeah, all is done. Now just make sure GPU runtime is running, which we just did, and just we'll start now. Alright, so we'll start by importing the required libraries, and once we've done the importing, yeah, I'm printing out this line just to make sure we're running TensorFlow like 1.15. So this is the version, and the detector version this one. All is good. Let's start with the installation of TFOD API. So to do the installation, what you need to do is first of all clone the repo, TensorFlow repo. So for that, we'll run this command git clone, and this is the TensorFlow TFOD API repo. So I'm gonna run this, and this is gonna clone the whole repo. It's like 600 plus MB plus. If you're running this on Windows, this would take some time, but if you're using Google Colab, then you're utilizing Google's very fast, like internet speed, and it will be done like that. I mean, almost like that. Or it's taking some time, but it will, yeah, it's done. See, so anyways, that's all done. 600 MB and just like that. And so now that the whole repo like is cloned up, I'm gonna open up like the folder. All right, so here's the issue. Like my pause and play bar is just overlaying the button to display the file. So I'm gonna zoom out, and I'm gonna like launch this, and then I'm gonna zoom back in. So once you clone this, you'll see this folder here, and this is the whole repo that like has the models and all the files. So we'll be going over inside this research directory. This is where the TFOD API is present, and we will be installing and making all the like installations here. So we'll be we'll be going inside this directory. You can also visit this, like I think here there are total 4 directories in this repo. So if you go here, so you'll see something like this, or the official repos, the research collection of research models. These are the official models. You can use any of the models, but there will be a model zoo that I'll show you later on that you will be using. So anyways, let's close this up and like proceed to the rest of the tutorial. So yeah, after like you have cloned the repo and you have that models directory in your Colab notebook, what you need to do is move into this directory. So os.chdr, I'm going to change the directory and move into this directory, and then I'm going to use this Protos compiler to compile all Proto files. So here's the thing, Proto files are some special sort of binary files that Google developed back in I think 2008. So these are some special binary files, and these are the files that will be present inside this directory. Object, you'll see that inside research you'll see a directory called object detection, and inside that you'll see Protos, and you'll see a bunch of files with an extension of .proto files. These are binary files that we will be needing when we're running the object detection, installing the object detection. So but we can't use .proto binary files. We need them in .py extension. So this is why we need to compile them, and to compile them you'll need this Protos compiler. In Windows, you will have to install it, and I have outlined a procedure how to like install the Protos compiler for your particular scenario. I mean, I think I have covered it here. So yeah, download Protos buff compiler. So this is where I show you, like how to download the required version of the Protos compiler and then use it. So anyways, but in Linux, I mean, when you have a Linux backend, life is easier. So you don't have to worry about that. It's already done with the Colab backend. So once the compilation is done, you'll see for every .proto file, you'll see a .py file generated after you run this piece of cell. and it will be present there. So once you run this command, you can go back to this location and you can check it out actually. After that is done, what we will do is that we will copy this setup.py file, and we'll paste it inside this object I think this directory. So we'll copy this setup file and we'll paste it here, and then we'll install this setup file. We'll run this setup file and it will do all the installations. So in Python you can either install with pip, you can install with by using the setup.py file. This is exactly what we're doing here. We're utilizing the setup.py file to make all the installations and configurations to make the object install the whole TFOD API. Finally, when the TFOD API is installed, we'll go back to the main directory, which is this TF object detection version 1 directory. So this is the main directory that we will go back to. So for that we have to move up 2 directories. So this is the syntax for that. So by the way, this is something that is really familiar to the person who works with Linux. So I'm assuming even people who are not that much familiar with the Linux interface, they will be able to follow along the whole tutorial. So anyways, I'm running this, and so just ignore this warning, and after this is run, the whole thing will be installed. So installing packager, TFSlim, object detection installed. Yeah, all is done. By the way, just as a side note, TFSlim is the backbone upon which TensorFlow object detection API is built. So in TF1 we use TFSlim, but in TF2 we use Keras. So I don't want to go into much detail to confuse you with this, but just this is just a side note that with TF1 OD API we use this as a backend, and this was used for a long time, but with TF2 we're using Keras. So anyways, it's all used internally, so you don't need to bother yourself with this. So now that we have installed this, all we need to do is build the API, and for that we'll be using this Python. We're calling this model builder tf1 test.py, and let me just run this first, and this will perform I think all the tests necessary to make sure everything is working fine. So these are all the tests, model builder tf1 test.py. So this will run several tests, and it will tell you if everything run fine, if the whole API was installed correctly or not. So if you see everything 21 test and 0 okay, everything's okay, everything ran fine, and we're all good to go. So now the whole TFOD API is configured and installed. So before diving into the data collection in the annotation part, just download this support folder. So I have created this support.zip file. So this zip file is basically a collection of few useful files that you will need inside this whole pipeline, and I've sorted them, and I've some of the files I've already created them, and some are helper files, and so I've compressed them all in a zip file and hosted it in this drive link. So you can download it in, with this, or by running this, it will be automatically downloaded and extracted. So this will be needed later on. So I'm gonna just run this. By the way, if you're just curious what's present inside this support.zip, just see this. So these are the things that are present inside this support.zip files. All the things are self-explanatory, and I'll be talking more about it when I go over the later parts of this tutorial. So back to this. So alright, so the support folder is downloaded. Now we're gonna move on to the data collection and the data annotation part 3. So here's what we're gonna do. We're gonna download a YouTube video, and this is the particular video I'm downloading for this tutorial is a Tom and Jerry. It's a short clip from a Tom and Jerry movie where I think Tom got a magic ring. So I watched this movie, I think maybe more than I think 1.5 decades back, 15 years ago I think. I think 10. I don't remember exactly. By the way, Tom and Jerry is still pretty cool. So you can, I do watch clips from time to time, not the whole thing. So don't judge me on that. So anyways, so you can download any other video, but for when you're running for the first time, just try to run it as it is. So you do not run into unnecessary errors. So later on you can make changes, you can work it on your own dataset, As I said, this is whole configured in a way that it works whatever you want it to work with. So I download a YouTube video, and this is the link for that Tom and Jerry video. Let me just show you this one. I think so. Okay, follow link. So this is the video, and it's the like 4 minute 11 seconds video, and yeah, so that is the video that we'll be downloading. And so I'm specifying the URL here. The video name will be tomandjerry.mp4, and it will be stored inside this support directory inside test images, tomandjerry.mp4. And I'm using PAFI. This is the syntax to download the whole video. So you initialize PAFI.new, you put inside the URL here, and you initialize the whole thing with here video.getBest. This syntax gets the best resolution for that particular video, and then this syntax downloads the whole video provided when you provide the file name. And there are several options with PAFI that you can do, and there's a whole documentation here. So see all the various things that you can do with this PAFI library. As I said, there was a bug with this library, and so someone just disabled the dislike option, and I forked that repo, put it inside, and I'm installing it from my directory, so to avoid that error. So anyways, it will work fine when you run this. So that is all. I mean, you need to do, just run this up, and when you do that, you'll see our tomandjerry.mp4 video downloaded here. Finally, what we'll do next is split this video into image frames. So as you know, any video is a collection of images, right? So if you have an animation sequence going on, obviously what's happening is that a bunch of images is being shown to you rapidly. So the greater the number of images, the higher the quality of the animation is, the more fluid it appears. So for example, a typical video is normally a 30 fps video or a 25 fps video. This particular video is a 25 fps video. So I know that because I have run this. So this particular video is at 25 fps, which means 25 images are being shown at each second. Now, if I wanted, what I could do is create a data set out of each frame, but that is totally unnecessary. I mean, imagine this. This is a 4 minute 11 seconds video, and if each second is at 25 has 25 frames, just do a multiplication of 25 with 4 minutes and 11 seconds, you'll end up with a lot of frames. I think I'll need to calculate that, but anyways, a lot of frames. So you don't need to get that. One of the reasons is you don't even need that much frames, because we're doing one, transfer learning, and two, if you do get all those frames, there will be a lot of noise, because ideally what we want is to detect Tom and Jerry, but there's a lot of background and all of the unnecessary frames, so there will be a lot of noise. And three, if you get a couple of 100 frames, you will need to annotate all of them, right? So because the annotation has to be done by you, so you don't want to download enough a lot of data, so you don't need to annotate all of that. So if you enjoy annotating the data, go ahead. I mean, because that is the most boring part of the whole pipeline. So anyways, so here's how I specify this directory: training images. This is where all the images will be stored after we have extracted out of the video. And now here I'm specifying when to extract each image frame. So I'm saying I need to wait for 1.5 seconds, and after each 1.5 seconds, extract a video frame. So, and this is, by the way, I mean, this is really good. I mean, this is okay. So I'm waiting for 1.5 seconds, and I'm extracting a frame and saving it. By the way, don't change this variable right now. Don't mess with this, because I'm already providing you the annotations, and it's configured in a way that it works exactly with this sort of setup. If you do make something changes here, you will run into problems. Those annotations will not be viable for you, because obviously, to follow along with this tutorial, I'm not asking you to annotate the data again. I'm providing you the annotations, and this is an automated data extraction process. So make sure to have all of this in exactly the same manner. This particular cell, I mean this data extraction part, have it. Don't mess with this unless you're gonna do annotations yourself and not gonna use my annotations that I'm gonna provide. So anyways, by the way, there are two ways to go about it. One is that you specify seconds. So I need, for example, I'm specifying 1.5 seconds. So after each 1.5 seconds, I'm gonna take a frame. After another 1.5 seconds, I'm gonna take another image. You can also do this. Skip 10 to 20 frames, and then after that, get another frame. Skip 30 to 40 frames. But I find it's more convenient, or more, like I can see it, because when I watched the video, I watched after how much time the frames stops over a character, how much background is there. So I feel that 1.5 seconds was enough to get good enough data. So anyways, that's why I went with that approach. So after specifying this seconds, I'm gonna get the FPS, and I'm then gonna do some calculations to understand how many frames I need to skip. So I multiply the seconds by the FPS to get the total number of frames I needed to skip in order to achieve this sort of a setup. Then I used OpenCV to to read frame by frame inside a loop, and I checked if the frame was read correctly. If if it isn't, break out of the loop, and this will happen when the video ends. Then I just grab the frame ID, and I then check if the frame ID is divisible by the number of frames to skip. If that is true, only then I'm gonna save the frame, and I'm gonna use CV to Imwrite to save out the frame. I'm also following a particular naming scheme. This is, again, you need to follow this because the annotation files are linked to this. So this is a naming scheme that I'm following. So after that, I'm gonna just append this frame counter, and then after the whole video has been read, I'm gonna just release the camera. This is the video capture object. So this is the video capture object which has been initialized, and I've passed in the video name, which is the, I think this is the video name here, right? Tom and Jerry .mp4. So anyways, so there is that. It's a really simple procedure, and I think I've done this when I was creating my video classification tutorial. Anyways, let's run this. When I'm running this, the whole data is being created automatically, and all right, so it's done. All is done. I mean, as you can see, the total number of images that are saved are 165. And let me show you these images. So these are all the images that you will get, and this is the sort of a format 00, 001, 002.jpg and stuff like that. And at the end you get this. As you can see, there's a bunch of noise. For example, I mean, there will be a couple of frames with the background. I think I've removed them. So maybe, yeah, as you can see, 87, 89. So I've removed, the frames. 88 was a messy frame. So once you get the data, normally what you do is you just remove the unnecessary frame before you do the annotation process. And this is done when you're doing the annotation process. So there's that. After you're done, you'll be left with these images which you can annotate. So anyways, the step 3 is the annotation phase, and you can use any annotator, but one of the most popular ones and most simplest one is this labelImg, which you can install by doing pip install labelImg. When you do pip install labelImg, you'll get, I also included a code, I think, installation step here. So this is here, pip install labelImg, and once you have installed it, you can launch the labelImg by just opening up your command prompt, and do something like cmd labelImg, just click enter, and the labelImg will pop open. So, and once it opens, you'll need to follow a particular simple procedure to annotate all the files, to draw bounding boxes around it. Let me show you, a whole video which I recorded on how to annotate all of this. So I think, where is it? So yeah, here is it. So now you'll be watching a video of how the whole annotation process works and how to annotate it. So here it goes.
So what you have to do is to go to your custom detection folder. Right now I have named this a new TFT detection, but when I provide you this folder, I will rename it to custom object detection, something like that. So after generating the training folder, and when you have generated the TFrecords, so what you will do is that you will create another folder here, and let's call it labels. Alright, so now what you will do is launch your command prompt in this directory like this. Activate that new TF2 environment. Alright, now launch the labelImg here by typing labelImg. Alright, So the labelImg is launched. Now before we start annotating the images, we need to set the directory from which we will load the images. So this is our open directory. Click on that, and then it's already selected because I previously did it. So you will select this directory, images, where all the images are stored. After selecting this, click on the select folder. Now your training directory is set. If I click on next, I can move on to all the images, and I can move back by clicking the previous. Alright, so our directory for the images is set. Now the second thing we have to do is change the save directory where the annotations will be saved. So I want the annotations to be saved on this labels directory. So I will click on this, and then I will click on select folder. So now what will happen is that every time I annotate an image, the annotations will be saved in that labels folder. So for example, I will click on this create and create box. This cursor will pop up, and I will annotate this head. Alright, it will ask me to put in a name. I'll put in Jerry. Alright, I'll click on OK, and then I have to click on this save icon. Alright, you have to do that. I click on the save icon. Now annotation is saved on that labels folder. I click on this next image and then annotate this image. I click on OK. So similarly, you have to annotate all the images. Alright, and then I'll click on save again, and the annotation will be saved. Alright, so you have to go through all the images. So for this image, there is no no Jerry or Tom, no class present. So I will just skip this image and annotate the other ones. Ideally, you may want to clean up your folder, maybe delete this image prior to labeling, but it doesn't matter, because the way the TFrecords generator which I have edited is, it will let you pass and skip all these non-annotated images. Another thing you have to make sure is that this is Pascal VOC, not YOLO format. If I click on again, then this will be saved. The images will be saved in YOLO format. So the labels will be saved in the YOLO format. Make sure this is Pascal VOC written here. Alright, so let me show you another example in which another class is present, which is Tom, I think. Alright, let's see if I can find a Tom image. So this is an imbalanced dataset. As you can tell, most of the images are of Jerry. I'll create this. This is Tom. I'll have to label it like this. So I'm not doing this, and the annotation I'm doing right now in front of you is not how you would do it. So for perfect results, you would predefine it. If you want to capture the ears, if you want if you want to get the neck, so the annotation should be done properly for best results. Right now, for the demonstration's sake, I'm not focusing on that. So if it's another class, I'll name it Tom, and I'll click on OK. And then I'll also annotate this with Jerry. So when I have two classes, it will give me an option, Jerry or Tom. So I don't have to type every time I annotate. So right now I'll just select either Jerry or Tom. I'll tell it it's Jerry. I'll click on Jerry, and then I'll click on OK. So this is how your whole workflow will work. And another thing, yeah, I forgot to save it. Yes, save this image. Alright, so another thing which I forgot to tell you is that you can even go back to previous annotations and edit it. So if I move on to the first annotation, see here, so I can edit this box and correct the annotations if I I incorrectly drew it. So you can go back to previous images and correct the annotations. So after you're done, just close this, and you can go to the labels folder, and you'll see XML files present there. The format would be like this. This would be the name of the image, and then there would be a .xml extension, and for each image you would find a single XML file. And if you click on these XML files, then where is it? Just give me a second. Alright, open the other monitor. Alright, so this is how the images annotations are stored in the XML file So like this is the name, this is the location, then these are the dimension xmin, ymin, xmax, ymax, and so this is how the XML format is stored. We will convert this XML format in TFrecords later on, but like right now this is how it's stored in XML. So yeah.
Alright, so back to the original tutorial. So now that you have annotated all the images, now we're going to create another file. Now this file is called a labelMap file. So all you need to do is just do this. I mean, this is the whole thing, whole content that's going to go inside this file. Basically, this file is required by the TFOD API, and it tells the model how to map IDs with the class names. So we have we have one class which is called Jerry, and the ID for that is 1. And because if we had another class, I'm gonna call it this one. I'm gonna call this one Tom, and the ID for this one is 2. If you just had one class, you will be getting rid of this. You will just have a singular ID. And if you had more classes, if you wanted to detect more objects, then you will just create another item just like this. This is like a dictionary in Python. So just add this, add another, increment this counter by 3, and create and pass it another name, whatever the thing you picked up. So by the way, this has to be the same name which you assigned when you were annotating the objects. So once you're done, just open the file labelmap.txt and write this text and put it here. You can do this manually. I've just created this whole collab notebook in a way that even the things that you need to do manually input in a text file, you can do that automatically here. So by by just adding this here and running this cell, labelmap.pbtxt will be created with the updated names. So anyways, let's run this. And so yeah, once that is done, we are almost done. Just one last step is remaining, and that is to convert the data annotation files, the .xml files, and the images into TFrecords. And this is a particular format, and TFrecords, by the way, is protocol buffers. It's the same thing, like the .proto files that you saw earlier. It's sort of the same thing. It's the same protocol buffers, and the reason we need to create these TFrecords is because it's a sort of a requirement to make it work with TFOD API. Normally, when you're training an object detection model, all you need are images and annotation files either in .json format or .xml format. But when you're working with TFOD API, it is a requirement that you work with TFrecords. That is why we have to create this particular format out of those data things that out of the data. And one of the reasons that Google went for this particular approach is that TFrecords are more efficient. So they are more computationally efficient in terms of transferring the data, reading from disk and whatnot. So they are computationally efficient, efficiency reasons to make pipeline and restrict the whole approach in a way that you have to work with TFrecords. So, and by the way, if you're interested in how to create TFrecords, because right now I'm just gonna call this script. So this is a script, create tfrecords.py, which I created by utilizing a bunch of other scripts and merging it in. So I'll tell you about it. But if you're interested in the whole process, because it's sort of like a dry process, how the TFrecords are created, what sort of syntax is used. It's an optional step if you're interested in how to, if you're interested in what parameters are passed, what happens internally, what sort of arguments you need to have to create TFrecords out of images, audio files, text, any other data type. So because this is something that it's not necessarily restricted to object detection. It's once you know how to create TFrecords of different data types, it's a useful skill. So for that reason, I have 2 tutorials. One is a detailed explanation of how protocol buffers work with an example, this one, and then there's a nice tutorial also that goes more in depth on TFrecords. So there are 2 tutorials which you can follow along if you want to learn more about it. Anyways, the script I'm using is this one. It comes with the support folder that you downloaded earlier. So create tfrecord.py, you pass in the image directory, you pass in the images, you pass in the labels, and you pass in the TFrecords. where the TFrecords will be outputted, and then the label map file, which you just created .pbtxt file, which maps the integers to the label names. So you just pass in these necessary things, 1 to 5 things, and after that, by the most interesting thing is this one, split percentage. So I am telling this whole script to use 80% of the data for training and 20% for validation. And one other thing, normally people when they create the data set, they split the data in that part. So they normally have 2 folders, one for the validation, one for the training. But here I've created a script such that it does 3 different things. So most of the scripts that you will find online will do 2 to 3 things. First, they will take your .xml files and convert them into CSV, and then they will use another script to split out the data, and then into training validation folder, and then another script to convert those into TFrecords. So what I have done is just created a single script that utilizes all these 3 things inside a single script and just do all of them in a single call. So that is all you need to do. Just run this and you're all set. You'll have the TFrecords. So yeah, now we're all set. You will find 2 files, train.record, val.record inside this folder TFrecords, which is inside this training folder. And yeah, so that's done. Now we have regarding the data annotation and creation part, we're all done with that. Now comes the model downloading and training part, which is I think the more interesting one. So here's the thing, go to this link, model zoo. Now this is the link, or this is the zoo or the garden, the thing that you can bookmark right away. So this is the page that will host that is hosting all the different sort of models that you can use inside TFOD API version 1. By the way, if you were using TFOD version 2, you would have even a lot more variety, even more robust models. But because we are using TFOD API version 1, we are restricted to these models, but these are also pretty good. So we have models we have SSD models, we have faster RCNN models, we have mask RCNN models. SSD and faster RCNN are object detection models, and you can tell by looking at this output column, and output are boxes, which means it is an object detection model. Mask RCNN also is a segmentation model. It provides you masks. So it gives you the mask, the outline of the object. So it's a segmentation model. And if you're interested in how much accurate these models are or how fast these are, so this is these, you can take a look at these 2 columns. So this is the speed in milliseconds. So the bigger the number, the more time it takes. So for example, this takes almost 2 seconds to work on a single image, but at the same time it gives you the highest or the best performance, mean average precision, MAP. So you can think of mean average precision as an accuracy. For example, in classifier you work on accuracy, but by the way, these are totally different things. So if it telling you that it has an 18 MAP, it doesn't mean it has an 18% accuracy. That would be really bad. But this is sort of a metric which has a whole different explanation. So it's a whole neat mathematical explanation how mean average precision is calculated. You will need to understand what IOU means, how that works. So I'm not gonna dive into how this whole thing is calculated, but just understand this: the higher this number, the better the model is in terms of performance and detecting the objects and accuracy and whatnot. So this is how this works. By the way, this is faster. If you are interested in the most powerful model, you will be using this, but just avoid that. And by the way, this is NAS, neural architecture research. So this has to be the best one, I think, in here, because of how this is how the architecture of this is designed, and it's an interesting theory. Anyways, without rambling upon the theory of this one, just gonna briefly cover some things about this. So by just reading the names of this model, if you know some bit of theory about deep learning, you'll know a lot about this one. So for example, you can take a look at this. You can understand this is an SSD MobileNet V2 model. MobileNet V2 is the base model. So when we normally work with object detection architectures, we have 2 parts. One is the architecture of the object detection, and one is the base model. So the better the base model, the better the whole mean average precision at the end would be. So consider this. MobileNet VNet is comparatively very computationally, like cheap. So, but it lacks, like performance. It lacks mean average precision. So you will see MobileNet VNet V1 is like 21 MAP with 30 FPS. But if you go all the way to V2 and MobileNet V2, you'll see like this thing bumped up to 22, and like not only is this a bit better in performance, but it's also like somewhat faster. So this is what you get. And then if you replace the MobileNet V2 with Inception model, so if you're interested in deep learning theory, you must have come across these models. So Inception, like ResNet. So we have also ResNet here. So we have like like Inception, we have ResNet 50, ResNet 101, and if you're also interested in which data this model is originally trained on, it's also written at the end, COCO. So this is the common objects in context. So this is the 90 class dataset which this model is trained on. So again, you can get a lot of information by just like reading the names of these models. So anyways, without boring you with all these unnecessary details, let's go back to this, and I'm gonna just pick a model, and I'm gonna be using faster RCNN model. This is the object detection architecture, and the base model that I'm using is this Inception V2 COCO. And so yeah, this is the whole name for this particular model. And the way I got to know the whole name was by going to the like model zoo. I think I just copied the link, and then I like look at the last part of the link. So if I do, I think something like this, then I can see here that this one is SSD Inception V2 COCO 2018 28 TAR GZ. So this is the like the model which I'm going to be using. So this is the exact thing, like the section of the URL which I'll be copying and then pasting it here, and I'll get rid of the last part. So that .tar.gz, I'll get rid of that part, because it's here. I'm like concatenating it here, so you don't need that part. So just for any model that you need to download, just grab that part, copy the URL, paste it, grab this part, paste it here, and you're all set. Now using this script, it will be automatically like downloaded from this repo. It will first of all, it will check if you're not downloading it again. If it is, it will remove the whole directory. So if you have trained the model, make sure to not run this again if you don't want to lose all those files. So anyways, once that is done, downloaded, we'll get rid of the zip files, and we'll remove them, we'll remove any unnecessary files, and finally we'll do this other thing, and this will remove this checkpoint file. And this is very important, because otherwise the training will not start. So this is important to get rid of this checkpoint file to make sure the model trains again on your particular data set. So now what I'm going to do is just run this up, and it's going to print model downloaded when it's done. So yeah, model has been downloaded, and we've just gone to this GitHub URL and like downloaded this model, and we've gotten rid of unnecessary files after that. Now if you check take a look at this file structure. So let me go over here and close this up. So we'll have, I think, where is it? Yeah, pre-trained model. So this is what we get: a saved model, a frozen inference graph.pb, model checkpoint, this one, CKPT index, CKPT meta. I'll be explaining about like all of these things later on. So this is sort of a particular all these files are like have an explanation. They're all important files like that you will need. So anyways, I'll be explaining about them later on when the time is right. But now what you need to do is you only need to be interested in this file, pipeline.config. Let me open this up. So this is the file which contains like all the information about the model, like what dimensions it accepts, like because faster RCNN uses the FCN block, it can work on various sizes. You just specify min dimension and max dimension. So the size is not, initial size is not restricted because of the CNN layer, the type of CNN layer that's used. So this is just something that you'll understand if you have studied that type of layer, FCN layer. So anyways, then we have this feature extractor. We are using faster RCNN in Inception V2. And then we have some other information, like the anchor generator that's being used, the regularizer, the L2 regularization is being used. And there are stages, different first stage, non-maximum expression threshold, IOU threshold, max proposals. So this means, like how many detections the model will output. So every time you make a detection, even if there is nothing present, it will give you 100 boxes. So if you need to control false positive rate, you need to change this variable. First stage localization loss rate. So a lot of different parameters, and don't just be overwhelmed with everything. I mean, in fact, I even don't know every single thing right away, right? I'll need to Google a couple of things, even if I need to, like understand what some things mean. There are a lot of different things, and only I don't even think the like the creators can remember every single argument that they put up here and the parameters for that. So it's okay to not understand many of these things here. Through time, once you understand the foundational theory of deep learning, over time you will understand these things. And not everything is that much important. I mean, some of the things you can leave it as it is, and then some of the things like you can tune it. If you understand, maybe tuning those part will improve the performance and whatnot. So like batch size is important. This is something you understand. Like how many you should tune, number of steps. Like something like that. How many number of steps you should like take, and stuff like that. So, anyways, all the things that we need to what we need to do right now to make the whole training work. And before we can start the training, is to change a couple of things in this pipeline.config file. Let me zoom back again. So these are the like 5 things that you will definitely need to change. All of them I think are pretty self-explanatory, but I'll just go over them. So the first one is the model.ckpt, the checkpoint file, and you'll change it to the pre-trained model.ckpt. So this is default paths that need to be configured. So these are just placeholder text. Part to be configured for the train.record, put in the actual part of the train.record, then put in the actual part of the well.record, then put in the actual part of the labelmap.pbtxt file that you just created above. Finally, also change the number of classes from 90 to 2, because the original model was trained on the Coco dataset of 90 classes, but your Tom and Jerry dataset consists of 2 classes, Tom and Jerry. So put it 2 here. Now you could go on to that file and just manually change these paths, but since we're lazy, I'm lazy, I can't speak for you. So I just created a Python script. So every time I use a different model and I have different parameters, different paths, I can just run this cell and it will configure and make all these necessary changes. So just, I'm reading the files and I'm using regex to substitute placeholder file names with these actual, with the real paths. So here's where all the, substitutions are done. And after this, you're all done. But there are a couple of other things that I'm doing. One is this one. So I'm changing this step 0 to step 1, and this is necessary to make it work for this particular model. So there was an error that I was getting when I was running fast RCNN, and when I googled that error, I found a GitHub issue and I landed with this solution. So and this is an issue with TFOD API version 1. I wasn't facing these issues when I was running the version 2. But in version 1, whenever you choose a different model, there's a particular issue that you face during the training phase. You get an error, and then you can copy and paste that Google error. But fortunately, every time you copy and paste Google error, you'll find a good GitHub issue that outlines what's missing. So it will tell you to change this particular thing in the pipeline.config. And once you do that, the training will start again if you run the cell again. So this is something that I needed to do to fix the error. Change the step 0 to step 1. And after that, one other thing that I'm doing is changing the batch size from 1 to 5. Now, if you were using a local GPU, now I can increase the batch size, but I know for a fact, I think if I increase it to maybe 10 or something, the Collab GPU will crash. So if you are using this locally and you have a high powered GPU, you can increase the batch size. This will speed up the training, significantly. But make sure to, don't go over the RAM of your GPU, because then it will crash. So you can work around, tune with what's the best batch value that's working for your use case. So anyways, let's do that. After we're done with that, the whole configuration will be done. So now after this, I think but just to repeat again, you can also change a number of other parameters in the pipeline.config, just as I showed you earlier. But for that, you will need to understand a bit of theory, how object detection architectures are created and what sort of parameters that should be changed. Otherwise, you'll be don't mess around with values that you don't know anything about, because then after the training, after hours of training, you'll find out like the model is not doing well because you just change an unnecessary variable. So anyways, obviously break the code. You'll learn that way, but be smart about it. So anyways, we'll start the training, and to start the whole training, you'll just run this command. So we have this Python file model main.py. This is the file that will start the training. You'll need to pass in just these three things: number of training steps, pipeline.config path, like the pipeline that we just configured over, the model directory. This is a directory where the whole output files will be like stored. So when the model has been trained and the new model is created, this is where the whole new things will be stored. So so the only thing I think I should explain is this number of steps. So remember, when you're training a classifier in TensorFlow Keras, you specify a number of epochs, and one epoch is when the model goes over and learns over the whole data set, right? So number of steps, train steps, is sort of a similar thing, and we also, I think, use this sort of a similar variable in those Keras training pipelines. So for example, a single training step is when you go over a particular batch. So if you have a batch size of like 5, so, and you have like, consider a batch size of 10. So when you do one training step, you go over those 10 image examples. And if you do 10 training steps, you will go over 100 image examples. And if your data set is like 100 images, so you will need to do 10 training steps to go have a full epoch, of the whole data. So I think a couple of thousand is number of training steps is most of the time is enough to train like over the whole data. And oftentimes I think it will also exit out itself, because there is a like breaking point somewhere that if the loss is not decreasing, break out of it. I don't remember seeing it in the pipeline.config, but I think it's present there. So anyways, all you need to do is specify reasonable number of training steps. A couple of thousand is okay. I've put 2000 here, and it also depends, like how big your batch size is, how many image examples are there. And yeah, so these are the some of the things that you should consider. And after that, I'm just gonna run this, and the training will start, hopefully not right away, but you will see a bit of configuration steps. But after that, the training will start. So this will take some time. I think for this particular data set, it takes about like, I don't know, maybe like 3 to 4 hours or something in this Collab GPU. Maybe if I go Collab Pro, it will be maybe a bit faster, I don't know. So anyways, if you have followed along this way, now you can rest a bit, and I'll just resume the video after the training is done, and we'll go over from there. So by the way, the training has started, and you can tell by looking at this line. So initially when we started, the step is 0. We started from step 0, and the loss is high. So it's like 4 point something. And as you see, as the time progresses, the loss will decrease. If it's not decreasing, you should, like something is wrong. You should check it out. So as you see in this just the first step, the loss decreased significantly from just 4. It went to like 0.581. The step was 100. So 100 steps were executed, and after each 100 steps, it's outputting logs of the whole, like what's happening. It took like 113 seconds when it ran 100 steps. And remember, one step is like using 5 images, so we have a batch size of 5. So, and yeah, so this is the loss that it got after doing the first iterations. So in the next iteration, we'll see somewhat decrease in loss, and similarly after several iterations, we'll see a decrease. All right, so now the training is done, it's completed. So you'll see it exited out at 11,500 steps. It stopped training, even though we specified like 2,000 steps. So the reason probably was, I think the loss wasn't decreasing by a certain margin in several steps. So you can obviously change these values to make it train on like the exact 2,000 steps. So anyways, I think this loss is a reasonable loss, 0.108. and it was just after like 11,500 steps, after I think approximately 3 hours of training. So now that we are done with the training, what we're going to do next is we're going to use this model, which is in a .ckpt checkpoint format. You can use this model to do predictions, but it's not the ideal format. Now this .ckpt model is mostly used for retraining the model or continuing the training later on with more data and different parameters. So you can do that, but what we're more interested in is creating an inference graph, a frozen inference graph. This is a different sort of a design of the same model. So it's again, it's a machine trained deep learning model, the same deep learning model here, but in a different format. So we'll be using this script to create and generate that frozen inference graph. For that, we'll be specifying this output directory, fine-tuned model. This is where we'll store the generated frozen inference graph, and we'll create this directory. And then what we're going to do is we're going to take the so when you train a model, you'll see that inside the training directory where we're storing the output formats. Let me show you the exact, I think where was it? So we're storing the output in this pre-trained model, right? So if you go inside this directory, you'll see several models, not just one model. So at every couple of 100 time steps or so, there's a, I think, limit. Maybe it's like a 10-minute period or maybe an iteration period. So there's a time period. So after every period has passed, a version of the model will be saved on the disk. And this is really good because suppose your kernel crashes, something happens, you have been running hours and hours of training. You don't want to lose restart the whole process again, right? So you want to continue your training later on when you can. So this is why at every period, I think, which is a time period or an iteration period, a version of a model is stored. And the best performing model is obviously most likely the latest version, right? So the last version. So this is what we're doing. I'm telling to go over this location and get the latest version, and it will be with an integer. I think the latest integer would be the latest version of the model, not CKPT version. Use this version to generate the frozen inference graph, and to generate the frozen inference graph, I'm going to be using this script, export inference graph.py. Now this is the script which generates the frozen inference graph, and you pass in just a couple of things the pipeline config file path, the train checkpoint prefix, which is like this one, and then the output directory where the thing will be outputted. So by just specifying these things, it will, when you run this, the frozen inference graph will be generated and stored in this output directory. The output directory right now is this fine-tuned model. So yeah, so let me show you how these files look like. So this is what this looks like after you've run this. I'm not going to run this right now, but I've already done this locally. So this is what the output looks like. You get this frozen inference graph.pb. And by the way, now we have three sort of different models. We have the checkpoint model, we have the save model format, and this is also has a .pb extension, but these are different things. This model is also deep learning model, which has been trained on raw data, but it's a different sort of format. By the way, this format is the one that's being used in the TF2 by default. But what we need actually is this model, frozen inference graph.pb. This is the actual model that we'll be using for this. And again, we have also this sort of a model checkpoint data format. And when you generate the checkpoint format, you also get these files. These are some files with the meta information regarding the model, or the architecture, design, stuff like that. So these are just the meta files, but this is the actual model in the checkpoint format. This is the model in the inference graph format, and this is the model in the save model format. All three of these models can be used to make predictions inside TensorFlow. But and just to recap, I'm going to show you how that is done. So you're going to scroll down below, and this is like a bonus step. Like this is where I'm going to just show you how to use the frozen inference graph inside TensorFlow to make predictions. Just test out the model. So I'm going to read up a sample image, test7.jpg. So I have some test images, there are a couple of, I think, 5 to 6 images, and these are something images that are not present in the original dataset. So you can use this to test out how the model is performing. Ideally, you will need a more descriptive test set to thoroughly test out the model's performance. but just for the sake of this tutorial, I'm checking it in 5 to 6 images. And I just have this bonus step where you can check how to, and this is the whole syntax that you need to run the model inside TensorFlow using sessions and graphs. So I'm just gonna run this. By the way, if you're not gonna bother with training the model, you can just use this. So inside, when you download this support folder, I also give you the frozen inference graph, which I created initially. So when I was training. So even if you don't want to bother with training, you can check this model out. Just run this and it will give you predictions. So I'm using OpenCV and TensorFlow to make predictions. But since this is not what I want, and most likely you will not be using this anytime in future, because sessions and graphs are in TensorFlow 1 are outdated. Normally we don't use that. We just use TF2 anyways, so as you can see, it's performing pretty well. We have Jerry with 90% accuracy, Tom with 74.5 to 5% accuracy, and so it's doing pretty well inside native TensorFlow. But this is obviously not what I want. We want to get rid of TensorFlow and use this frozen inference graph directly in OpenCV. And to do that, I think it's now relatively really simple, because we have the frozen inference graph. The only other thing that we need, and it's not exactly strictly necessary, but for this particular tutorial it is, because otherwise it won't work and it will give you some issues, is that something that we need to generate something called the graph.pbtxt. And this is not the same file that we created above. So remember that we created a .pbtxt file above. That was a different file. It's not this one. So this is a file that is OpenCV specific, and to generate this file you need Python script that is provided by OpenCV. So OpenCV provides these 4 scripts: tf text graph ssd.py, faster.rcnn.py, mask.rcn.py, and efficient.py. These are graph generator files, and these are the files that you need to use to generate graphs. And which exact file you will be using depends upon the model that you used. So we trained the model on faster RCNN. Remember, this is just the object detection architecture. So if we use an inception model, we'll still be using this faster RCNN model. If we use some other faster RCNN variant, we'll still be using this particular Python file. So this is a Python script that generates a file called graph.pbtxt, which is a requirement by OpenCV, and it's just helps the OpenCV in understanding the architecture of the model, some rewiring a couple of layers. So it's just something that OpenCV needs to work with TensorFlow properly. You can also skip this model in some cases, but for the most part you will be needing this file. So there are some scenarios where you don't even need this. OpenCV will just work with the frozen inference graph off the bat, but for most of the scenarios you will need this. And so you can go over this link. So this is the link where you will find all of these 4 files, and whichever model you used, because we use faster RCNN, I'm going to be using this file. By the way, if you downloaded the support folder with when you cloned it, you'll have access to this file. So you'll have access to this one and this one too, SSD and faster RCNN. You'll have access to both of them. So right now you don't need to do anything extra, but just understand this, that we have linked this repo or link here where you can go and download these files. And as I said, there are a couple of things, maybe some short details that I'm not brushing up upon, but when you go over the blog post and when you read it, make sure to go over them. So because otherwise this whole tutorial will become a lot drier, if it's not already. I hope it's not. So anyways, once you have generated the graph.pbtxt file by running this, I'm not going to run this because I already have this one. Now you're all set to use this model directly inside OpenCV. So now we have 2 files. We have the OpenCV's, we have the frozen inference graph, and we have the pbtxt file. And remember, when you were using this DNN module inside OpenCV, we use 2 files. We have the pbtxt file and we have the frozen inference graph, and this is exactly what we'll be doing here. So what I'm going to do is just run this, and this is the initialization function. Here I'm just passing the configuration file as .pbtxt. I'm passing in the frozen inference graph, the path to the exact frozen inference graph, and then what I'm going to do is let me just going to change the path, I think, because I'm going to change this to support. All right. Because don't change this to support when you run this, because I'm just doing this right now because I skipped the training in mid. I didn't completed the training in the ideal way I should. Anyways, once you do that, OpenCV's DNN module will read from these files. So it will read the model, it will read the configuration file, and then you'll create this dictionary for the object detection. 0 is Jerry, 1 is Tom, and so once you're done with this and you have read the files, all the initialization will be done. And then what you need to do is create another function called detect object, pass in the image, and this is the threshold 70%. So if the confidence is above 70%, only then I'll draw the bounding boxes, otherwise I'll skip it. So this is something that you can control. It's up to you. I think I'll just set it to 60. And anyways, so yeah, so after that what we're gonna do is we're gonna get the rows and columns of the image. We're gonna use blob from image to do the exact pre-processing steps that we did initially. So right now I'm reading the image. I'm swapping the red blue channel equals to setting it to true, because in TensorFlow we work with RGB, OpenCV we work with BGR, so we need to swap the channels. So I'm setting it to true. If we were using a cafe model, we will not need to do that because cafe itself work with BGR. So we setting it to true, and optionally I'm just setting the size as 800 by 800. This is just to make sure. Remember, we used a faster RCNN model. By using a faster RCNN model, we were not restricted to a specific size because of a specific FCN layer that is used inside that network, and that layer just has some criteria that it's just markers that make sure your minimum size is above 600, your maximum size is below 24. 800 passes both of those things. It's just something. You can also work with different sizes, but make sure you can also do center crop equals to true to maybe check out if it's performing better or not. The better the pre-processing steps that you perform, the better the the results you will get. So this is just a very rough pre-processing step that I did. Ideally, this is not, if I wanted to get the best performance out of this, I will not have resized it to a fixed 800 by 800. I will make sure to center crop this image and make it the best possible aspect ratio to get the maximum the best output. So I'll do some stuff like that, but just for this tutorial I'm skipping all of that. I'm just resizing it to a fixed 800 by 800. I'm creating this blob. Once I have this blob, I'll just set it as the input, net.setInput blob, and then I'll run this net.forward. Remember, this is the same workflow that we already have done multiple times. After setting net input, we are setting the net.forward path, and this will give the output. So this is where all the object detection outputs are stored. Then we are going to iterate over each of the detection, and then we're going to extract the probability, the score of for each detection by doing this too. And then we're going to check if the probability that is detected is above a certain threshold confidence, which we specified as 60%. If it is, then we're going to get the class index. This is the index 0 or 1, Tom or Jerry, and then by using that index we're going to get the name by using the dictionary that we created above, Tom and Jerry dictionary. And then we're going to grab the x1 y1 x2 y2 coordinates, so columns rows. So we're going to get that, and then once we have that, we're going to multiply them by the columns and rows, the actual columns and rows of the images, because when you get the predictions, you will get the columns and rows coordinates in a 0 to 1 range, and these are not the actual coordinates, but they are compressed in 0 to 1 range. To get the actual values out, you will need to multiply the 0 to 1 range values with the actual columns or the width and the height of the image. Then you will get the actual coordinates. Once you have the actual coordinates, you can use cv2.rectangle to draw out the boxes, and once you're done, we'll show the output in matplotlib. If we have returned data equals to false, this is when I'm working with videos. I'll just return the image. I'm just going to initialize this again, and again I've explained all of the things that are returned here. So because we're not working with batches, we get the first one, because for every detection we get these 7 attributes or 7 parameters. The last 4 are the x1 y1 x2 y2 coordinates. The first one is 0 because we're working with a single image. If we passed in a batch of images, then we'll have an array where each index correlates to a particular image in the batch. And then the next one is the index of the class, and the third one is the score or the confidence or the probability of the class. So these are all the 7 attributes that you get. Make sure to again read this go over all of this tutorial after watching this video and read this. This is something that took us a lot of time to create. So this I know, I remember for a fact that I think this tutorial at every out of all the blog posts or videos tutorials I've published, this one took the most effort, and this took a lot of time to get this right, because this is something that nobody was doing, and there were a lot of things that we faced when we were lot of errors to get this right. So I needed to get this, because I know how useful this was, and how people need to understand how to directly link TensorFlow with OpenCV and merge them in a way, and create that workflow. Anyways, without babbling this on and on, let's finally just initialize this by calling the initialize function. So I just ran this and I faced an error. So the reason was I was using some incompatible versions. So when I was using my stored in frozen influence graph on the support section from the support folder, I should have also used graphrs.pbtxt file, which was generated in the previous run. So either use both of these or both of these. So yeah. So if you want to use your own custom trained model, which you just trained above, use this. Otherwise, if you want to use the model which I trained, use this. So after doing that, when I ran this, it worked perfectly fine. And now we're gonna see the fruits, of our work in action. Hopefully, this will work. And yeah, so it's running. So yeah, Jerry 44%, and see this one. Okay, Tom 99.5%. Okay, that's working fine. As I said, I will talk about some certain limitations with this one, and it's good. Okay, so Tom 99%. Then one final image. All right, this one. Tom 81.2%, Jerry 97.65%. So it's really good. These images, obviously, I picked out these images. So if you just go over the internet and pick up a couple of others, there will be issues, and there are reasons for that. So it will work on a couple of other images, but it might not work on other images. And there are a couple of reasons. So there are 4 different reasons which I would like to stress upon. And one of the reasons is that transfer learning normally works best when you have retrained a model on a similar data set with similar qualities. So the Coco data set and the other one were trained on real world images, the actual images. But right now we're leveraging this model to work on animated characters, and that sort of a shift is a drastic shift. So you can get issues in this sort of a transfer learning approach, and you can mitigate this issue by including more examples of these animated samples. So if you use more and more examples and you train further layers, then you'll get better performance in this whole approach. The other reason is the animations across different movies of Tom and Jerry is not consistent, right? So in different Tom and Jerry series and movies, the animators use different styles and techniques. So even though the things might not be clear to the eye, there are drastic differences in the type of animation. So that might be another issue. Then the images that we generated with our automatic generation way is a very rough approach. I mean, if you needed higher quality data, you might have used some other approach. You might have scrape the internet, then scroll around. That might be even better approach. So scrape the internet, get Tom and Jerry images across various animation styles and whatnot. Then maybe clean the data, get the model on it. But that's something that will require several steps, right? So instead of bothering with that, I just went for a minimalistic approach. It worked fine, but it can be better when you use the scraping sort of an approach. Now the other thing was, I think the Jerry images were a lot more than Tom images. Now this is an issue. Now you can have class imbalance. You can make the model be aware of that there is class imbalance, and you can give weightage to a different class. You can't go around, but it's better to have more examples of that class if you want it to work perfectly. So that is another thing. The other reason is the annotation was poor. I mean, when I was annotating this, I just roughly annotated every example image, and you can see this by the fact that I see the face is above the hair, and the face, the box is going above here, And then yeah, it's not the perfect annotations, and one of the reasons is that I didn't bother making the annotations be perfect. So there need to be standards in place when you're training a production model. All right, so these were the issues related to the accuracy. Now there are a couple of other issues in this whole approach in general. So one of the issues is that if only use this approach when you're fully dead set on using the final model inside OpenCV. If this is not something that much important to you, I will strongly recommend that you ignore this approach and just go with TensorFlow 2, because TensorFlow TFOD API version 2 is really like a massive improvement with version 1. There are a lot of bug fixes, there are a lot of improvements, there are a lot of better models. The backend whole is built upon Keras. It's a lot different. As I said, I can still go about all of the different things you can do, all of the things in a whole day. In fact, I can create a whole course on it. So I'm not gonna bother with that right now, but just gonna tell you that if object detection is the only thing that is your concern, go with TensorFlow Object Detection API version 2. Or if you're interested in PyTorch, go with Detector on True. So those are the best two frameworks for creating custom object detection models across a variety of tasks, right? Object detection is similar high level deep learning task, right? So other than that, the other thing I think was that, yeah, the custom model that you're training with TensorFlow version can give you sometimes issues, like if you're trying to make a different sort of a model work, and that is mostly when the graph.pbtxt file is not working fine with the OpenCV and there are some version conflicts. So at those times you will need to diagnose the issue and inside and open the graph.pbtxt file, make necessary changes, and you'll need to understand what's happening inside those files and how they work to make those changes, because it's something really advanced, and that can happen when you're trying to make it work with difficult object detection models, and something that is not covered here, stuff like that. So there are some caveats there to look upon. Or finally, one thing that I deeply miss is the thing that is that the save model format, which is the default of TensorFlow 2, does not work with OpenCV. Hopefully over time, through time, OpenCV will provide support that save model formats work with OpenCV, and if that happens, then it gets better, because then you can use TensorFlow 2 TFOD API directly with OpenCV DNN Module. But I don't know when will that happen, and I published this blog post a year back, more than a year back, I think 1 to 5 years ago, and I'm recording this video tutorial later on in 2021, at the end of 2021, and I think it's still not supported. I didn't Google that much if it's supported or not, but from what I understand, it's still not there yet. I have to look upon the change logs of OpenCV to make the final verdict, but I do think it's safe to say it's not fully supported. So anyways, I think this is the most comprehensive course out there on deep learning with DNN module, how to leverage everything that you need, and there's a lot more to it. If you go over the blog post, all the 3 blog post descriptive ones, go over the notebooks, understand fully how this works, how the nitty-gritty details and whatnot. Maybe I will also be creating a couple of other tutorials on DNN module, like on super resolution, emotion recognition, and some others maybe I have in mind. I don't know for sure right now what will I be creating in future. It depends totally upon what's the demand of it. Finally, one last thing that you should encourage you to do is enroll in this computer vision for building cutting edge applications course. It's a premium course that's coming real soon. If you're watching it at the end of 2021, then it's coming real soon, and if you're watching it in the next year, earlier next year, then it's already out there. So make sure to enroll in this one, and some very amazing interesting applications I'll be showing you how to build, something that's not out there, something that's totally different and really interesting. So do look out for that. And I think that is it for this course. I hope you enjoyed it. If you did, do please let me know in the comments. I love to hear you out, and if you feel there are some issues, do point that out, and but just let me know if this was useful to you by liking this video, commenting on it, maybe sharing it with your colleagues. So that is all for this video, and I'll see you in the next one. Bye.